Europa has long fascinated scientists with its gleaming surface, hidden ocean, and tantalizing possibility of life. Now, the James Webb Space Telescope, humanity's most powerful eye on the cosmos, has turned its gaze toward this enigmatic satellite, peering into the frozen depths of a mysterious world, light years away, and uncovering secrets that have been locked beneath ice for billions of years, and capturing details no telescope has ever seen before. In this video, we'll dive into the astonishing discoveries Webb has revealed, uncovering clues that bring us closer than ever to answering one of the universe's most thrilling questions: could life exist on Europa? Before we start this journey, let us know where in the world you're watching from and what time it is for you right now. Drop it in the comments below and settle in for a journey to unravel what lies beneath Jupiter's icy planet. The James Webb Space Telescope, often called JWST for short, is one of the most ambitious and extraordinary tools ever created by humanity to explore the universe. Its story begins long before its launch, with decades of planning, technological development, international cooperation, and a vision to look deeper into space and further back in time than any telescope that came before it. The JWST is not just another space telescope. It is a giant leap forward in humanity's quest to understand the cosmos, to uncover the secrets of the early universe, to study the formation of stars and planets, and to explore worlds far beyond our own solar system. Its very existence represents a marriage of human ingenuity, scientific curiosity, and the relentless drive to push the boundaries of knowledge. The idea of a next-generation space telescope was first conceived in the 1990s, shortly after the success of the Hubble Space Telescope. Hubble had given humanity breathtaking views of distant galaxies, nebulae, and star clusters, providing a window into the universe that was never before possible. However, scientists quickly realized that while Hubble was revolutionary, it had limitations. Its primary mirror, while powerful, was relatively small at only 2.4 meters in diameter, and it was optimized mainly for visible and ultraviolet light. Many of the most exciting phenomena in the universe, such as the earliest galaxies, newly forming stars, and the atmospheres of exoplanets, emit much of their light in the infrared spectrum. To fully understand these objects and events, a new telescope would be required, one that could observe in the infrared with unprecedented sensitivity, clarity, and resolution. This is where the concept of JWST was born, a telescope capable of observing the faintest light from the earliest epochs of the universe, when the first galaxies were forming, more than 13 billion years ago. Planning for JWST was a monumental task that spanned decades. It involved scientists, engineers, and administrators from around the world, working together to design an observatory unlike anything previously attempted. One of the first major challenges was the primary mirror. To collect the faint infrared light from the distant universe, the mirror had to be much larger than Hubble's. The JWST's primary mirror was designed to be a staggering 6.5 meters in diameter, almost 3 times larger than Hubble's. However, such a large mirror could not fit into a conventional rocket fairing, which led to one of the most remarkable engineering feats in the history of space exploration. The mirror had to be designed to fold up like a delicate piece of origami, so that it could fit inside the rocket for launch, then unfold perfectly once in space. The mirror itself is made up of 18 hexagonal segments, each precisely engineered and coated in a layer of pure gold to enhance its ability to reflect infrared light. The gold coating, while only a few hundred nanometers thick, significantly increases the telescope's sensitivity to the heat emitted by distant celestial objects. Another significant challenge was the telescope's need to operate at extremely cold temperatures. Infrared detectors are highly sensitive to heat, and even the tiniest warmth from the telescope itself could overwhelm the faint signals from distant galaxies. To solve this, JWST was designed with a massive sunshield the size of a tennis court, composed of 5 thin, reflective layers of a special material called Captain. This sunshield protects the telescope from the heat of the sun, Earth, and Moon, allowing its instruments to cool down to near absolute zero temperatures. The cooling is crucial because it allows JWST to detect the faint infrared light from objects billions of light years away without interference from its own thermal radiation. The sunshield alone is an engineering marvel, capable of being folded into a tiny package for launch and then deployed precisely in space, layer by layer, to form a protective barrier against the sun's heat. JWST's location in space is also carefully chosen. Unlike Hubble, which orbits Earth at a distance of about 500 kilometers, JWST operates from a point nearly 1.5 million kilometers away, at what is called the second Lagrange point, or L2. This location offers a stable environment with minimal interference from Earth's heat and light, allowing the telescope to maintain its extreme sensitivity to infrared light. L2 is a gravitationally stable point in space, meaning that JWST can orbit around it in a relatively steady manner, with minimal fuel usage to maintain its position. This remote vantage point is both a blessing and a challenge, as it allows for incredible observations but makes maintenance impossible. Unlike Hubble, which astronauts could repair and upgrade during servicing missions, JWST had to be designed to operate flawlessly for at least 10 years without human intervention. The scientific instruments on board JWST are another testament to human ingenuity. There are 4 primary instruments, each designed for specific tasks, yet all working together to give an unprecedented view of the cosmos. The near-infrared camera, or NIRCam, is the telescope's primary imaging instrument, capable of capturing detailed pictures of distant galaxies, nebulae and stars. It can observe light that has been stretched into the infrared spectrum by the expansion of the universe, allowing astronomers to see galaxies that formed only a few 100 million years after the Big Bang. The near-infrared spectrograph, or NER spec, takes this a step further by splitting light into its component colours, allowing scientists to determine the chemical composition, temperature, density, and motion of stars and galaxies. The mid-infrared instrument MIRI extends JWST's capabilities further into the mid-infrared range, enabling it to observe the faint glow of distant dusty galaxies and study the atmospheres of exoplanets in incredible detail. Finally, the fine guidance sensor and near-infrared imager and slitless spectrograph, or FGS NIRIS, helps the telescope maintain precise pointing, while also allowing specialized observations such as detecting the tiny dimming of a star as an exoplanet passes in front of it, which can reveal the planet's size and atmospheric properties. JWST is not just a technological marvel, it is also a product of global collaboration. NASA led the project, but significant contributions came from the European Space Agency, which provided the NIRSpec instrument and a crucial part of the Sunshield deployment system, and the Canadian Space Agency, which contributed the EFRAS-NIRIS instrument. This international effort demonstrates how science can unite countries and agencies around a shared dream, the pursuit of knowledge about the universe we inhabit. The telescope's construction involved thousands of engineers and scientists across multiple continents, each contributing their expertise to a single goal: to unlock the mysteries of the cosmos. The launch of JWST was itself a story of anticipation and tension. Originally planned for launch many years earlier, the telescope faced numerous delays due to the complexity of its design and the unprecedented technological challenges it posed. It finally lifted off on the 25th of December, 2021, aboard an Ariane 5 rocket from Europe's spaceport in French Guiana. The launch on Christmas Day was a historic moment, symbolizing hope, curiosity, and human achievement. After a month-long journey through space, the telescope arrived at its destination near L2 and began a carefully choreographed series of deployments. Over several weeks, the mirror segments unfolded, the sunshield layers stretched into place, and the instruments cooled to their operational temperatures. Each step was meticulously planned, with engineers on Earth monitoring the telescope's every move, knowing that any error could jeopardize the entire mission. Once fully operational, JWST began to deliver images and data that exceeded even the most optimistic expectations. Its first observations revealed galaxies in astonishing detail, showing structures and formations that had never been seen before. Scientists could, for the first time, observe the light from some of the earliest galaxies that formed in the universe, mere hundreds of millions of years after the Big Bang, a time when the cosmos was still in its infancy. These observations are helping astronomers answer fundamental questions about how galaxies evolve, how stars form, and how the elements necessary for life are created and distributed throughout the universe. JWST also enables the study of exoplanets in unparalleled detail. By analysing the light that passes through a planet's atmosphere, astronomers can detect the presence of gases such as water vapour, carbon dioxide and methane, which could indicate the potential for life or the conditions necessary for habitability. In one remarkable observation, JWST captured the spectrum of an exoplanet's atmosphere, revealing a complex mix of molecules that had never been measured with such precision. In addition to studying distant galaxies and exoplanets, JWST is shedding light on phenomena closer to home, within our own solar system. Its infrared capabilities allow it to peer through dust clouds that obscure young stars in formation, to examine the surfaces and atmospheres of planets, moons and asteroids, and to study the faint glow of objects in the outer reaches of the solar system. For example, the telescope has observed the ice-covered surface of Jupiter's moon Europa, revealing tantalizing hints about its potential subsurface ocean and the possibility that it could harbour life. JWST's observations of Saturn, Neptune, and even distant Kuiper Belt objects are providing new insights into the formation and evolution of our solar system, helping scientists understand the processes that shaped Earth and its neighbours billions of years ago. Beyond its scientific achievements, JWST represents a story of human perseverance and creativity. The project faced countless challenges over its decades-long development, from technical setbacks and budget overruns to the inherent difficulty of building a telescope that could survive the harsh environment of space, while performing measurements with extraordinary precision. Engineers had to invent new materials, design novel deployment mechanisms, and develop instruments that could operate at temperatures near absolute zero, all while ensuring that the telescope could remain perfectly stable and accurate over millions of kilometers of distance from Earth. The successful deployment and operation of JWST is therefore not only a triumph of science, but also a testament to the human spirit, our willingness to dream big, to tackle seemingly impossible challenges, and to achieve what was once considered beyond reach. JWST's impact on science is already immense, and its potential for the future is even greater. By peering deeper into the universe than ever before, it is helping to answer some of the most profound questions in astronomy. How did the first galaxies form? What are the conditions necessary for life to exist elsewhere in the universe? How do stars and planets evolve over time? Every image and spectrum it captures brings us closer to understanding the universe's past, present and future. Moreover, JWST is inspiring a new generation of scientists, engineers and explorers. Its discoveries spark curiosity, ignite imaginations, and remind us of the vastness and beauty of the cosmos, encouraging people everywhere to look up and wonder. Jupiter, the giant of our solar system, has always fascinated humans, from the earliest stargazers who first noticed its wandering light in the night sky, to the sophisticated space probes of the modern era. Its immense size, nearly 2.5 times that of all the other planets combined, makes it a remarkable object of study. However, Jupiter's own composition, a gas giant made mostly of hydrogen and helium, while fascinating, is only part of the story. Equally, if not more, intriguing are the moons that circle around this enormous planet, particularly the icy ones. These moons, including Europa, Ganymede, Callisto and others, are not just tiny satellites moving in orbit. They are worlds with potential secrets that could fundamentally change our understanding of the solar system and life itself. The significance of studying these icy moons is vast, encompassing the fields of planetary science, astrobiology, geology, chemistry, and even the future of human exploration. Jupiter's icy moons are compelling primarily because they offer a glimpse into environments vastly different from Earth, yet under conditions that might be suitable for life. Unlike the rocky terrestrial planets such as Earth, Mars or Venus, these moons are covered in thick shells of ice, which in some cases conceal oceans of liquid water. Water, as we understand it, is the essential ingredient for life, and the presence of liquid water beneath the frozen surfaces of moons like Europa makes them tantalizing targets in the search for extraterrestrial life. Europa, for example, is slightly smaller than Earth's moon, yet it is believed to contain a vast global ocean beneath its icy crust, perhaps containing more water than all of Earth's oceans combined. This idea transforms our perception of where life could exist, suggesting that it may not be limited to planets within the habitable zone, where temperatures allow liquid water on the surface, but could also thrive under ice, shielded from harsh radiation and cosmic conditions. The study of these icy moons is significant because it challenges our understanding of planetary formation and evolution. Each moon has a unique story written in ice and rock. Ganymede, the largest moon in the solar system, is even bigger than Mercury, and it has its own magnetic field, which is unusual for a moon. Callisto, heavily cratered and ancient, preserves a record of impacts stretching back billions of years, acting as a time capsule of the early solar system. Studying these moons allows scientists to compare them, to understand how bodies in orbit around a massive planet can develop differently under similar conditions. This knowledge is crucial for constructing models of how planets and moons form, how they evolve, and how their surfaces and interiors change over time. One of the most fascinating aspects of Jupiter's icy moons is their dynamic nature. Although they may appear as cold, lifeless orbs from afar, these moons are anything but static. Tidal forces, generated by Jupiter's immense gravitational pull, flex and stretch these moons as they orbit the planet, generating heat inside their interiors. This process, known as tidal heating, is believed to keep subsurface oceans in a liquid state despite the frigid temperatures on the surface. The ice may crack and shift, creating surface features like ridges, fractures, and chaos terrains, particularly evident on Europa. These constantly changing surfaces are natural laboratories for studying geological processes under conditions unlike those on Earth, revealing how heat, ice, and water interact to shape planetary bodies over time. Studying these moons also has profound implications for astrobiology, the science that seeks to understand the origin, evolution, and distribution of life in the universe. For decades, the scientific consensus was that life needed conditions very similar to Earth's: warm temperatures, a stable atmosphere, and sunlight. The discovery that moons like Europa or Ganymede may harbour oceans beneath layers of ice radically expands the range of potential habitats for life. Scientists speculate that chemical interactions between water and the rocky cores of these moons could provide energy sources sufficient to support microbial life, even in the absence of sunlight. This possibility is more than just science fiction. It motivates missions designed specifically to detect signs of life, such as molecular markers, unusual chemical ratios, or even direct evidence of microorganisms. The technological challenge of exploring these moons underscores their importance. Missions to study Jupiter and its moons must overcome intense radiation belts, extreme cold, and vast distances from Earth. For context, Jupiter is approximately 480 million miles from the Sun, and a spacecraft travelling there takes years to arrive. Instruments must be able to survive harsh conditions, penetrate ice, analyse subsurface oceans, and relay information back to Earth across immense distances. The development of such technologies not only pushes the boundaries of engineering but also prepares humanity for future exploration of other distant worlds. The knowledge gained from these missions can be applied to studying other icy bodies in the solar system, such as Saturn's moon Enceladus, Neptune's moon Triton, or even distant objects in the Kuiper belt. There is also a historical and philosophical dimension to the study of Jupiter's moons. Ever since Galileo Galilei first observed the four largest moons, Io, Europa, Ganymede, and Callisto in 1610, he opened a new chapter in human understanding of the cosmos. These moons, once mere points of light in the night sky, are now recognised as complex worlds worthy of detailed investigation. The continued study of these moons connects us to centuries of curiosity, observation, and the enduring human desire to explore the unknown. Each new discovery, whether it is a subsurface ocean, a geyser of water vapour, or a complex magnetic environment, expands our sense of possibility, challenging our assumptions about where life could exist and what conditions are necessary for a habitable world. The significance of studying these moons also extends to understanding Jupiter itself. The giant planet's gravitational influence affects the orbits, geological activity, and even the atmospheres of its moons. By studying these satellites, scientists gain insight into Jupiter's formation and its role in shaping the solar system. For example, understanding how tidal forces influence Europa's icy shell can inform models of planetary formation and migration, shedding light on how Jupiter acquired its moons and why they differ so significantly from one another. In this way, the moons serve as keys to understanding their enormous parent planet, creating a more complete picture of the complex interactions within planetary systems. Recent missions and observations have only heightened the importance of these icy worlds. The Galileo spacecraft, which arrived at Jupiter in 1995, provided a wealth of information about the planet and its moons, revealing evidence of subsurface oceans and intense geological activity. More recently, the Juno mission, which entered Jupiter's orbit in 2016, has offered detailed measurements of the planet's magnetic field, gravity, and atmospheric dynamics, indirectly informing our understanding of the moons. The upcoming missions, such as the European Space Agency's Jupiter Icy Moons Explorer, scheduled for launch in 2025, promise to investigate the surfaces, ice shells, and potential oceans of these moons in unprecedented detail. These missions are designed to detect the composition of ice, analyze the chemistry of surface materials, and study the potential habitability of subsurface environments. The cumulative effect of these investigations is to transform our understanding of the outer solar system from a distant and mysterious realm into a scientifically rich landscape full of dynamic worlds. The icy moons are not only scientifically valuable, but also potentially economically and strategically significant for future human exploration. Water, in the form of ice or liquid, is a critical resource for sustaining life beyond Earth. It can be split into hydrogen and oxygen for rocket fuel, or used directly for drinking and growing food. Establishing a presence near or on these moons could provide resources for long-term missions deeper into the solar system, such as exploring Saturn, Uranus, Neptune, or even sending probes to interstellar space. In this sense, the study of Jupiter's moons is not purely academic. It lays the groundwork for humanity's future as a spacefaring civilization. Moreover, these moons provide a natural laboratory for testing theories about planetary processes in extreme environments. For example, studying the interactions between ice, water, and rock under high pressure and low temperature can teach us about geophysical and chemical processes that cannot easily be replicated on Earth. Observing active geology, such as surface fractures or plumes of water vapor, gives clues to the energy dynamics within these moons. Understanding these processes improves our models of planetary science and contributes to our knowledge of Earth itself, particularly in areas like climate science, oceanography, and geophysics, where extreme conditions can produce parallels to processes occurring on our home planet. The cultural and inspirational significance of exploring Jupiter's icy moons should not be underestimated. Humanity has always looked to the heavens for wonder and insight. The idea that there could be oceans beneath frozen crusts so far from the warmth of the sun sparks imagination, fuels curiosity, and encourages generations to pursue science, technology, engineering, and mathematics. From science fiction writers envisioning life beneath the ice, to educators inspiring young minds with the possibility of distant oceans, these moons capture the human imagination and remind us that the universe is full of surprises waiting to be discovered. Among the countless celestial bodies that orbit our Sun, few have captured the imagination and curiosity of scientists and space enthusiasts, quite like Jupiter's icy moon Europa. While Jupiter itself, the giant among planets, commands attention with its massive size, swirling storms, and the iconic Great Red Spot, it is Europa, a relatively small moon, that holds an almost mystical allure. The fascination with Europa is not just about its surface, its smooth, icy exterior, or its orbit around the largest planet in our solar system. It is about what lies beneath that icy shell, an ocean of liquid water that could very well harbour conditions suitable for life. This alone makes Europa a prime candidate for exploration, and understanding why requires a journey through its discovery, its unique characteristics, the science behind its potential habitability, and the missions that humanity has planned to unlock its secrets. Europa was discovered over 400 years ago, in the year 1592, by the famous Italian astronomer Galileo Galilei, alongside three other large moons of Jupiter, Io, Ganymede, and Callisto. These four moons, now collectively called the Galilean moons, were among the first celestial bodies discovered orbiting another planet, and their discovery fundamentally changed our understanding of the cosmos. But Europa has stood out among them ever since, largely because of the peculiar smoothness and brightness of its surface. Unlike other moons that appear cratered and scarred by countless impacts, Europa's surface seems almost pristine, as if it has been resurfaced over and over again. This characteristic suggested to scientists that there might be ongoing processes below the surface, and it was this thought that first led to the idea of a subsurface ocean. Europa is not a giant in comparison to our planet. Its diameter is about 3,100 miles, which is roughly the same as the distance from New York City to Los Angeles and back. While this makes it smaller than our moon, Europa's size is still large enough to hold a vast amount of material beneath its crust. Its mass is only about 8% of Earth's, but this is not a limitation when it comes to its scientific intrigue. In fact, the combination of a relatively small size with the intense gravitational pull of nearby Jupiter creates extraordinary conditions. The gravitational forces exerted by Jupiter and the subtle tugs from the neighbouring moons produce what scientists call tidal flexing. Essentially, Europa is stretched and squeezed by the immense gravity of Jupiter as it travels along its elliptical orbit. This constant flexing generates heat within the moon's interior, enough to keep water beneath the icy surface in a liquid state, potentially forming a global ocean hundreds of miles deep. This process of tidal heating is crucial because it creates an environment where life could exist, even far from the warmth of the sun. The icy surface of Europa is striking in both its appearance and its clues to the moon's inner workings. From images sent back by spacecraft, scientists have observed a network of dark streaks and ridges crisscrossing the moon like a spider's web. These lines, known as lineae, are thought to be cracks in the ice where warmer material from below has pushed upward. Some of these ridges stretch for thousands of miles, with widths spanning several miles, and they often appear slightly raised or displaced, indicating that Europa's ice shell is not a solid, unchanging mass, but a dynamic and shifting layer. There are also areas where the ice seems to have broken apart and refrozen, creating what scientists describe as chaos terrain, a jumbled patchwork of ice blocks of varying sizes, which suggests that subsurface water may have welled up and refrozen. Each of these features offers tantalizing evidence that Europa is geologically active, making it an exciting target for missions seeking to understand the possibility of extraterrestrial life. Beyond the surface, the notion of Europa's subsurface ocean has been supported by multiple lines of scientific evidence. Measurements from the Galileo spacecraft, which orbited Jupiter from 1995 to 2003, revealed that Europa has a magnetic field induced by its parent planet's strong magnetic environment. This suggests that beneath the ice lies a layer of electrically conductive material, almost certainly a salty liquid ocean. Calculations indicate that this ocean could be as much as 60 to 90 miles deep, far deeper than Earth's average ocean depth of just over 2.5 miles. If this ocean truly exists, it would contain more than twice the volume of water found on Earth, offering a vast potential habitat for life. Some scientists even speculate that the chemical ingredients for life, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, could be present, delivered by the water-rock interactions at the ocean floor, similar to the hydrothermal vents on Earth's deep ocean floor. These vents on Earth are teeming with life despite the absence of sunlight, relying on chemical energy to sustain complex ecosystems. If similar conditions exist on Europa, it raises the thrilling possibility that life could exist in environments far removed from our terrestrial experience. Europa's allure as a prime target for exploration is also amplified by its accessibility relative to other potentially habitable worlds. While Saturn's moon Enceladus also harbours a subsurface ocean and geysers that shoot water into space, Europa's larger size and closer orbit to Earth make it somewhat easier to reach for spacecraft. Moreover, the scientific questions that Europa poses about water, chemistry, geology, and the potential for life make it an essential stop in humanity's quest to understand life beyond our planet. Scientists are particularly interested in whether the ocean beneath Europa's ice is in contact with a rocky seabed. This interaction could allow for complex chemical reactions, including those that produce energy sources capable of sustaining life. Understanding Europa's chemistry could therefore provide insights not only into this moon itself, but also into the conditions under which life might arise elsewhere in the universe. In pursuit of these questions, humanity has already begun sending missions to Jupiter and its moons, with more ambitious missions planned for the near future. The Galileo spacecraft, which arrived at Jupiter in 1995, was the first mission to conduct detailed studies of the Galilean moons, sending back invaluable data about Europa's ice shell, magnetic field, and potential ocean. Sending back invaluable data about Europa's ice shell, magnetic field, and potential ocean. Following Galileo, the Hubble Space Telescope has provided remarkable glimpses of Europa from orbit around Earth. In 2009, scientists using Hubble detected faint plumes of water vapor erupting from Europa's surface, reminiscent of geysers, suggesting that the subsurface ocean might occasionally escape into space through cracks in the ice. This discovery fueled excitement, as these plumes offer a way to sample Europa's ocean without having to drill through its thick ice sheet. The next generation of exploration is being spearheaded by NASA's upcoming Europa Clipper mission, scheduled for launch in the mid-2020s. This spacecraft is designed to make multiple flybys of Europa, carrying an array of sophisticated instruments to study the moon's ice shell, composition, magnetic field, and potential plumes. The Europa Clipper will map the thickness of the ice, search for subsurface lakes, and analyze the chemistry of the surface and any erupting material. Each flyby, conducted from relatively close distances, will provide data far beyond what previous missions could achieve, allowing scientists to construct a detailed picture of Europa's environment. Alongside Europa Clipper, there are discussions about future lander missions that could touch down on the ice surface, drill through the outer shell, and directly access the ocean below. These missions could be humanity's first opportunity to search for life beyond Earth in a potentially habitable environment within our solar system. The potential for discovering life on Europa is not mere speculation. It is grounded in decades of research and our understanding of life on Earth. On our planet, life thrives in extreme conditions, from deep-sea hydrothermal vents to acidic hot springs, from Antarctic ice sheets to arid deserts. These discoveries have expanded the definition of habitable environments, showing that life can exist wherever liquid water and a source of energy are present. Europa fits these criteria in remarkable ways. Its ocean, kept warm by tidal heating, its possible chemical interactions at the seafloor, and the delivery of essential nutrients through the ice above create a plausible setting for life. Even if life is not present today, studying Europa could reveal the chemical precursors of life, shedding light on how life might arise on other worlds. Europa's story is also a testament to the evolution of human curiosity and technology. From Galileo's first telescope in 1592, which revealed Europa as a small, bright dot near Jupiter, to the complex spacecraft and telescopes of the 21st century, humanity's ability to explore and understand distant worlds has grown exponentially. Each discovery builds on the last, creating a chain of knowledge that brings us ever closer to answering one of the most profound questions: are we alone in the universe? Europa, with its hidden ocean and mysterious icy surface, stands at the center of this quest, embodying both the promise and the challenge of interplanetary exploration. Moreover, Europa offers a natural laboratory for studying processes that may be common across the universe. Water is one of the most common molecules in space, and ice-covered moons with subsurface oceans may exist around countless other giant planets in our galaxy. By studying Europa in detail, scientists can develop models for understanding similar moons around other stars, known as exomoons, some of which may also host oceans beneath their icy crusts. In this sense, Europa is not just a target for exploration in its own right, it is a window into the broader possibilities of habitable worlds in the cosmos. The scientific, philosophical, and even cultural significance of Europa cannot be overstated. It represents the boundary between the known and the unknown, the familiar and the alien. Its icy surface conceals a deep, dark ocean that could hold answers to questions humanity has pondered for millennia. What forms of life, if any, might survive in such an environment? How does a world so far from the warmth of the sun maintain the conditions necessary for liquid water? And perhaps most profoundly, what can Europa teach us about the universality of life itself? Each of these questions drives the interest in Europa and fuels the ambition behind the missions that will explore it in the coming decades. Jupiter is truly the giant of our solar system, a planet so immense it almost defies imagination. If you could somehow scoop up Earths, tiny as they seem compared to Jupiter, and fill this colossal ball with them, it would take nearly 1,300 of our worlds just to fill it. And at the very heart of this gas giant, the heat is staggering. The core reaches temperatures of about 43,000 degrees Fahrenheit, hotter than anything we can naturally experience on Earth. Yet for all its size, Jupiter is not a place you could land on. There is no solid ground beneath those swirling clouds. Instead, if you tried to descend, you would be plunging into a dense, roiling atmosphere. Everywhere you looked, clouds would stretch endlessly in every direction. Rich shades of brown, yellow, red and white swirling past in wide, flowing bands. These bands are what give Jupiter its unmistakable striped appearance, making it look like a planet constantly in motion. The deeper you go, the stranger it gets. The planet's atmosphere, mostly made of hydrogen and helium, becomes so compressed under the immense weight above that it turns into a thick metallic-like liquid. Far below that, at the centre, lies Jupiter's mysterious core. Scientists are not sure exactly what it is. It could be a molten, slushy mixture, or perhaps a dense rock weighing 14 to 18 times as much as Earth. It is a place of extremes that challenges our very understanding of what a planet can be. Then there is Jupiter's crown jewel, the Great Red Spot. This legendary storm has raged for centuries in the southern hemisphere, a furious vortex that has become the planet's signature feature. Its upper clouds rise more than 5 miles above the surrounding atmosphere, and the storm itself stretches about 1.3 times wider than Earth. When the James Webb Space Telescope trained its instruments on Jupiter in the year 2017, it revealed that this storm plunges at least 200 miles deep, 30 to 100 times deeper than the deepest oceans on our planet. And that might not even mark the full depth of this gargantuan tempest. The Great Red Spot is colder at its top than the surrounding clouds, dropping to a frigid minus 234 degrees Fahrenheit. Yet paradoxically, right above this storm, temperatures soar to nearly 2,400 degrees Fahrenheit, hotter than molten lava on Earth. Scientists suspect that the storm's relentless turbulence generates waves, both gravitational and acoustic, that heat the air above it. Curiously, the bottom of the storm is warmer than its top, an odd inversion that defies our usual experience of storms on Earth. Humans have observed this swirling monster for more than 150 years. At one point, astronomers feared it might be dying, shrinking, and losing power. But to their surprise, data from the Hubble Space Telescope showed the opposite. Winds along the edges of the storm have been steadily increasing, gaining about 1.5 miles per hour each Earth year. That may sound small, but these edge winds already roar at nearly 400 miles per hour, far faster than the fiercest tornadoes on Earth. Meanwhile, if you were somehow drifting in the centre of the Great Red Spot, you might feel a gentler breeze. The winds there are much slower, hiding the storm's full fury. No one truly knows what fuels this eternal storm. On Earth, storms weaken when they pass over land, but Jupiter has no land at all. Its atmosphere is a churning, dynamic sea of hot gases rising, cooler gases sinking, twisting and colliding, creating a storm system on a scale far beyond anything we know. Many scientists think the Great Red Spot began when several massive storms merged into one enormous vortex. Today, it sustains itself by pulling in cooler gas from below, hotter gas from above, and even swallowing smaller storms that wander too close. The storm's roots remain hidden beneath layers of dense clouds. Some have speculated about volcanic activity deep within, but Jupiter's composition as a gas giant makes that highly unlikely. The storm's striking colours, from soft salmon to deep brick red, remain another puzzle. One idea suggests a layer of colourless gas deep below reacts with the sun's ultraviolet light to create the red shades, but the truth remains unknown. The mystery endures. Jupiter is not alone in hosting titanic storms. Saturn too produces its own massive tempests, most famously the Great White Spot. This storm appears roughly once every 30 years, beginning as a bright concentrated patch in the clouds, and then stretching to encircle the entire planet. Scientists believe it is a huge system of thunderstorms, with lightning flashing more than 10 times each second at its peak. What powers the Great White Spot remains uncertain. Some think it draws energy from the sun, while others suspect a hidden heat source deep within Saturn itself. The Great White Spot, sometimes called the Great White Oval, is among Saturn's most astonishing and mysterious weather events. It mirrors Jupiter's iconic storm in shape, yet while Jupiter's storm has endured for centuries, Saturn's eruptions are fleeting, erupting in violent bursts every few decades. These enormous storms shine brightly against Saturn's golden clouds and are so vast they can be seen from Earth with even a modest telescope. Some stretch across several thousand kilometers, large enough to swallow our planet multiple times. In the years 2010 to 2011, the Cassini spacecraft, orbiting Saturn since 2004, witnessed one of these epic outbursts firsthand. Astronomers called it the Northern Electrostatic Disturbance, for the intense radio and plasma interference it created, and also the Great Springtime Storm, as it erupted as Saturn's northern hemisphere entered spring. Cassini's instruments discovered astonishing shifts, sudden drops in acetylene, surges in phosphine, and an unexpected temperature decrease at the storm's core. Even after the storm's visible clouds faded in 2012, the planet continued to release energy. Two huge hotspots merged, sending a vast plume of heat and ethylene into space, a dramatic aftershock to an already mighty event. These colossal storms follow a rhythm, often appearing every 28.5 years, when Saturn's northern hemisphere tilts most toward the Sun. They usually occur when the planet's position in its orbit corresponds to a solar longitude between 90 and 180 degrees. However, the 2010 storm broke the usual pattern, erupting unusually early, just after Saturn's equinox. Astronomers have officially recorded 6 great white spots in total. Medium-sized storms, called synoptic scale storms, sometimes appear in between these great events and may be related. For instance, in 1994, a storm observed both from Earth and by the Hubble Space Telescope appeared in Saturn's northern hemisphere and may have been linked to the 1990 Great White Spot. Before 2010, many storms formed in a region nicknamed Storm Alley, in Saturn's southern hemisphere, around 36 degrees south. Between 2002 and 2010, several of these storms flared up. The first in early 2004, the second in late 2004, nicknamed the Dragon Storm, and the third in early 2006, observed by astronomers Eric Bondu and Jean-Luc Duvergne. Each lasted for months, showing just how dynamic and unpredictable Saturn's weather can be, even in the vast cold reaches of our solar system. Another long-lasting storm began in late 2007 and rumbled on through the first half of 2008. By 2009, the southern storm alley was so busy that storms seemed to erupt almost without stopping, right up until the 2010 Great White Spot appeared, but this time in the northern hemisphere. During the Voyager 2 spacecraft's flyby in 1981, scientists saw a northern version of Storm Alley, located between 33 and 38 degrees north, right where the 1903 and 2010 Great White Spots would later appear. Curiously, no southern Great White Spot has ever been seen. This might be because Saturn's southern hemisphere is harder to see from Earth. But that is about to change. Between the years 2025 and 2038, the southern hemisphere will tilt toward Earth, giving astronomers their best chance yet to spot one. If such a storm behaves like its northern cousins, the next southern Great White Spot might appear after May 12, 2032, when Saturn's south pole points most toward the Sun. The first known Great White Spot of the telescope era appeared in 1876, and it was amazing, visible even with very small telescopes with lenses only 60 millimeters wide. Why none were recorded before then is a mystery, much like the puzzling century-long gap in observations of Jupiter's Great Red Spot in the 17 and 1800s. The storms usually start as small, bright patches but grow quickly, stretching across the planet. The Great White Spots of 1933 and 1990 both grew so much that they wrapped completely around Saturn. They form a head that swells in just a few days to more than 10,000 kilometers wide, kicking up a turbulent wake that circles the planet. The great storms of 1990 and 2010 rose 40 to 50 kilometers above the surrounding clouds and shone more brightly than the rest of Saturn's atmosphere. This brightness suggests that the storm clouds were covered in freshly churned water ice. Early in the 1990s, computer models suggested that these storms are triggered by thermal instability, a kind of tipping point in the atmosphere. But in 2015, two planetary scientists from Caltech suggested a deeper explanation. As Saturn's upper atmosphere cools with the seasons, heavy water falls out first, making the upper layers lighter. Then, as cooling continues, the remaining hydrogen and helium become heavier again. When this heavy layer breaks through to the layers below, the instability sparks a giant thunderstorm. The delay between the coldest season and the storm explains why they don't happen right after winter. Jupiter, they say, doesn't get storms like this because it has far less water vapour in its upper atmosphere. The head of the 2010 Great White Spot was made of about 55% ammonia, 22% water ice, and 23% ammonium hydrosulfide. The water ice was brought up from about 200 kilometres deep in Saturn's atmosphere by strong rising currents. This storm also produced an unusually high amount of lightning, about 10 bursts per second, compared to just a few bursts per second in smaller Saturn storms. Saturn's bright rings block our view of the planet's northern hemisphere from Earth during its winter solstice, so historical records have gaps. But Cassini, which arrived shortly after Saturn's winter solstice in 2004, gave scientists the first chance to watch these storms unfold in detail, showing a drama that is part science, part space art, and part pure chaos. Let's take a trip to the far reaches of the solar system and visit Pluto, the largest known dwarf planet we have discovered so far. This icy world is small, lonely, and far away, yet its atmosphere is surprisingly impressive. It stretches far above Pluto's frozen surface, forming more than 20 thin layers stacked like a giant invisible cake. Each layer is unbelievably cold and tightly packed, holding on to precious bits of gas in the darkness of space. By the way, our own moon also has something scientists call an atmosphere, though in its case it's so thin that it's almost nothing at all. This ghostly shell of gas, known as an exosphere, contains helium, neon, and argon. But here's the wild part. It is about 10 trillion times less dense than Earth's atmosphere. That's so thin it's almost nothing, like a whisper compared to a hurricane. While travelling through the vastness of space, you should always watch for black holes. These cosmic monsters are areas where gravity is so strong that nothing, not even light, can escape. Imagine a trap so perfect that even beams of light, the fastest things in the universe, get caught forever. But black holes are not always quiet. Sometimes they erupt like a space volcano. When they do, they don't spew molten rock, but unleash huge blasts of pure energy. These outbursts can tear great holes in the surrounding clouds of gas and dust, leaving empty spaces in the cosmos. Not long ago, astronomers spotted one of the largest cosmic craters ever recorded. Using powerful radio and X-ray telescopes, they discovered a supermassive black hole that had thrown a cosmic tantrum a very long time ago. This violent event took place in a galaxy cluster about 390 million light-years from Earth. The crater left by this ancient blast is so huge that you could fit 15 entire Milky Way galaxies inside it. Try imagining that. It's like fitting 15 oceans into a single drop of water. As you continue your imaginary journey through space, be careful where you land. Some worlds look harmless from far away but hide terrifying secrets. Take K2141b, for example, a planet that orbits a star outside our solar system. At first glance, it might seem a little like Earth. It has vast oceans, clouds, and even rain. But there's a shocking twist. These oceans are made not of water, but of molten rock. The surface of K2141b is a blazing hell, covered in seas of lava that plunge dozens of miles deep. In the daylight, temperatures rise to around 5,000 degrees, hot enough for the molten rock itself to boil into the atmosphere. Then, violent supersonic winds, rushing at nearly 1 mile per second, carry this vaporized rock across the planet to its cooler night side. There, the fiery vapor cools, turns back into liquid, and falls from the sky as rain. But instead of water, it's raining molten stone. The fastest wind ever officially recorded on Earth was linked to a huge hurricane. It happened on the 10th of April in the year 1996, when Tropical Cyclone Olivia hit Barrow Island in Western Australia. At its strongest, the storm lashed out with winds equal to a Category 4 hurricane, reaching an incredible 254 miles per hour. That's faster than a Formula One car at full speed, And unlike a race car, you can't just pull over when it comes toward you. You can only imagine the destruction such wind can cause. Roofs ripped off, trees snapped like matchsticks, and heavy objects thrown around as if they were toys. The only kind of windstorm faster than this is a tornado. Inside one of these violent whirlwinds, the air can swirl at around 300 miles per hour. But here's the problem. No measuring tool has ever survived inside such a storm to give an exact number. Weather instruments are destroyed in seconds, and just in case you're wondering, sticking your finger up to measure the wind is an even worse idea, unless you are okay with losing your arm. Or worse. To put this in perspective, here are some other wind speeds. A typical blizzard moves at about 35 miles per hour. A strong thunderstorm pushes the wind to around 50 to 60 miles per hour. A full tropical hurricane becomes dangerous once the wind is faster than 74 miles per hour. And then there are the truly mind-blowing storms, ones that reach up to 400 miles per hour. These speeds don't happen on Earth, but if you go to Jupiter, you'll find them. On Jupiter, the Great Red Spot is a giant storm swirling in the planet's southern hemisphere. The upper edges of this storm tower are more than 5 miles above the surrounding clouds, and the whole storm is almost 3 times wider than Earth. Recently, scientists discovered that this massive vortex stretches more than 200 miles down into Jupiter's atmosphere. That's 30 to 100 times deeper than Earth's deepest oceans. And those are just the safe estimates. The real storm may go even deeper. The Great Red Spot is colder than the rest of Jupiter's atmosphere. In the upper cloud layers, temperatures drop to a bone-chilling minus 234 degrees Fahrenheit. But closer to the core, the planet gets much hotter. The highest temperatures ever recorded on Jupiter were found directly above the Great Red Spot, where the heat can reach a staggering 2,400 degrees Fahrenheit, hotter than molten lava on Earth. This extreme heat may come from the storm's own violent movements, which create strong gravitational and sound waves that heat the atmosphere. Interestingly, the base of the storm is warmer than its top. If you stood in the storm's calm center, you might not feel much wind at all, but at the edges the winds rage at speeds of 300 to 420 miles per hour, faster than even Earth's strongest tornadoes. For comparison, on Earth, a wind of just 60 miles per hour is strong enough to lift a person weighing about 170 pounds off the ground. At 75 miles per hour, trees can be ripped from the ground, roofs peeled away, and mobile homes flipped over. At 150 miles per hour, even cars can be thrown through the air. Imagine then the unimaginable destruction the Great Red Spot could cause if it ever appeared on our planet. Thankfully, that could never happen. Earth simply doesn't have the conditions needed for such a storm. Studying Jupiter's Great Red Spot has always been one of the most challenging and fascinating pursuits in the field of astronomy. Scientists have long been captivated by this gigantic swirling storm, but observing it is no simple task. The main challenge begins with the planet itself. Jupiter is a world of unimaginable size and power. To give a sense of scale, Jupiter is more than 1,000 times larger than Earth and weighs over 300 times as much. It is a true giant in every sense of the word. Unlike Earth, which has a solid surface to stand on, Jupiter is a gas giant, meaning it is composed almost entirely of hydrogen and helium. Beneath its thick, colourful clouds lies an enormous ocean of liquid hydrogen, churning and circulating around the planet's hidden core. There is no solid ground to slow things down or stabilise the atmosphere, and this is one of the reasons why the Great Red Spot has been spinning endlessly for centuries without ever stopping. The storm itself is a massive example of the powerful forces at work in Jupiter's atmosphere. On this planet, heat and motion create a dynamic and complex system of rising and sinking gases. Hot gases from below ascend, while cooler gases from above descend, creating enormous circular currents. The result is a series of giant storms far beyond anything seen on Earth. Astronomers believe that the Great Red Spot likely began when multiple enormous storms merged together, forming one colossal cyclone that has persisted ever since. Over time, this storm has kept itself alive in an almost supernatural way. It continuously draws in cooler gases from the lower layers of Jupiter's atmosphere while also feeding on hotter gases from above. Smaller storms that wander too close are often absorbed into its massive circulation. Each time it engulfs another vortex, the storm gains more energy, growing in size and strength. In a sense, the Great Red Spot feeds on other storms in the same way a forest fire consumes nearby trees, leaving nothing behind but a larger, more powerful blaze of motion and colour. Yet, despite centuries of observation, much about the Great Red Spot remains shrouded in mystery. Jupiter's dense cloud layers prevent scientists from seeing clearly into the lower atmosphere, forcing them to rely on indirect measurements, theoretical models, and spacecraft observations. Could there be something solid beneath the clouds, like a volcano or a rocky core? Probably not. Unlike Earth or other rocky planets, Jupiter lacks a crust that could fracture or release molten material. Its interior is almost entirely gaseous, or liquid hydrogen, under extreme pressure, so any volcanic activity is impossible. Even the famous colour of the storm remains enigmatic. The Great Red Spot does not have a single unchanging hue. Its shades shift over time, appearing white or pale salmon at certain moments, then bright orange, and at other times deep brick red. One leading theory suggests that deep below the visible clouds lies a layer of a chemical called ammonium hydrosulfide. This substance could interact with energetic particles from space, known as cosmic rays, or with ultraviolet light from the sun, producing the storm's striking red colour. However, this explanation is far from confirmed. For now, it remains a tantalising hypothesis, one more mystery swirling within the already perplexing storm. Astronomers have been observing Jupiter's Great Red Spot for nearly 2 centuries in a systematic way. Continuous records date back to the early 1830s, but historical accounts show that the storm has existed far longer. The very first recorded observation came in the year 1665, when astronomers described a permanent spot spinning slowly within Jupiter's atmosphere. This means that the storm has raged on for nearly 400 years, far longer than any storm on Earth could survive. For comparison, the most intense hurricanes on Earth may last only a few weeks or months, while the Great Red Spot has endured through centuries of planetary weather. Despite its incredible longevity, the storm is now changing. Observations in the 21st century show that the Great Red Spot is gradually shrinking. By the year 2019, astronomers noticed that pieces of the storm's outer edges were breaking away, almost like shreds of paper being torn from a larger sheet. These fragments eventually faded into the surrounding atmosphere, leaving the storm smaller than it had been for centuries. Scientists predict that if this trend continues, by the year 2040, the iconic oval shape of the storm might disappear entirely, either becoming perfectly circular or vanishing from view altogether. Interestingly, as it shrinks, the Great Red Spot is also reaching higher into Jupiter's upper atmosphere. At the same time, its colour seems to deepen and intensify, taking on a richer, more vivid orange than ever before. The exact reason for this change is still unknown. Scientists suspect it may be due to chemical reactions taking place as fresh gases from Jupiter's deeper layers rise to the surface, altering the composition of the upper clouds and amplifying the storm's signature hue. While the Great Red Spot may be Jupiter's most famous storm, it is not the only one of enormous size. The planet hosts many other vast whirlwinds, including a smaller yet fierce anticyclone known as the Little Red Spot. Though smaller than its famous sibling, this storm is still a mighty force within Jupiter's turbulent skies. Recent observations have revealed that winds inside the Little Red Spot can reach nearly 400 miles per hour. To put that in perspective, such speeds exceed those of most commercial jets and could obliterate any object caught in their path. These winds are a reminder that Jupiter's storms operate on scales almost impossible for humans to fully comprehend, dwarfing even the most intense storms on Earth. Meanwhile, further out in the solar system, Saturn hosts a storm that is even more astonishing. Known as the Great White Spot, this colossal tempest makes Jupiter's famous storms appear almost modest in comparison. The Great White Spot initially appears as a bright, gleaming patch in Saturn's dense, hazy atmosphere, but it does not remain small for long. Within weeks, it expands dramatically, stretching across the planet in a luminous ribbon that eventually wraps all the way around Saturn. The site is so vast that the entire planet Earth could fit inside the storm's sprawling outline, emphasizing the scale and power of this cosmic phenomenon. The Great White Spot does not appear often. It typically forms only once every 30 years, coinciding with the times when Saturn's northern hemisphere leans toward the Sun. Scientists believe that these seasonal changes trigger the storm's eruption, much like seasonal shifts on Earth influence hurricanes and monsoons, but on a far grander scale. What begins as a small bright spot can transform into an enormous system of thunderstorms, with lightning flashes striking more than 10 times every second. Imagine an entire planet illuminated by continuous, crackling lightning, a never-ending strobe of energy that seems almost alive. The energy driving the Great White Spot remains a topic of intense study and debate. Some scientists suggest that sunlight alone may be sufficient to power the storm's violent winds. Others point to the patterns in Saturn's cloud layers, arguing that the storm is fueled by a deep internal heat rising from the planet's core. This hidden furnace could provide the enormous energy needed to sustain a storm of such unprecedented scale, feeding the Great White Spot from far below the clouds. The combination of sunlight, seasonal changes, and internal heat makes Saturn's storms some of the most complex and awe-inspiring weather systems known to science. Returning to Jupiter, the Great Red Spot and its smaller companions remind us of the incredible diversity and scale of weather beyond Earth. These storms are not merely scientific curiosities, they are living laboratories, revealing how planetary atmospheres behave under extreme conditions. The swirling gases, powerful winds, and shifting colours all offer clues about the composition and dynamics of gas giants, helping scientists to understand not only Jupiter and Saturn, but also the thousands of exoplanets discovered in distant star systems. Some of these distant worlds may host storms far larger and stranger than anything in our own solar system, making the Great Red Spot and the Great White Spot valuable benchmarks for comparison. Despite centuries of study, both Jupiter and Saturn continue to surprise and challenge astronomers. Each observation reveals new mysteries: the shrinking yet intensifying Great Red Spot, the Little Red Spot's extraordinary wind speeds, and Saturn's periodic eruption of the Great White Spot. These storms teach us that planetary weather can operate on scales and timescales that dwarf anything experienced on Earth. They remind us that even familiar celestial bodies like Jupiter and Saturn are full of surprises, with atmospheric phenomena that defy expectations and imagination. In many ways, the Great Red Spot has become a symbol of the sheer power and longevity of nature's forces. Centuries of observation have shown that even in a world dominated by hydrogen and helium, where there is no solid surface and conditions are extreme beyond comprehension, a storm can endure and evolve, shifting in size, shape, and colour. Its survival for nearly 400 years, combined with its gradual changes in the 21st century, offers a glimpse into the complex and dynamic nature of giant planetary atmospheres. In contrast, Saturn's Great White Spot serves as a reminder that not all giant storms are eternal. Its dramatic eruptions appear only every few decades, yet when they do, they dominate the planet's atmosphere with incredible intensity. The combination of scale, periodicity, and raw power makes it one of the most extraordinary weather phenomena in the solar system, rivaling anything on Jupiter and capturing the imagination of scientists and stargazers alike. Ultimately, the study of these storms is a testament to human curiosity and ingenuity. For nearly 2 centuries, astronomers have watched, measured, and theorized about the Great Red Spot, building a detailed understanding of its dynamics, even as it continues to evolve. They have combined observations from Earth-based telescopes with spacecraft missions, such as Voyager, Galileo, and Juno, to reveal insights about the storm's winds, chemistry, and behavior. Yet, every new observation also raises more questions, highlighting the limits of our knowledge and the endless mysteries of the cosmos. The Great Red Spot and the Great White Spot are more than just storms. They are living symbols of the planets themselves. They demonstrate the extremes of nature, the power of atmospheric forces, and the beauty of phenomena that span thousands of miles. They remind us that the solar system is not a quiet or static place, but a dynamic arena of motion, energy, and transformation. As we continue to study them with ever-improving technology and spacecraft, we are likely to uncover even more astonishing details, from chemical reactions hidden deep in the clouds to winds that surpass the speed of sound and lightning that could rival any storm on Earth. The discovery of salt deposits on distant worlds is one of the most fascinating and important achievements in modern space science. and it holds clues not only about the history of these worlds, but also about the potential for life beyond our own planet. Salt is more than just a seasoning we sprinkle on our food. It is a chemical fingerprint, a record of interactions between water, minerals, and environmental processes. Detecting salt on faraway planets or moons is a sign that water, in some form, may have been present, or perhaps still exists, and that the surfaces of these worlds are not static but dynamic, changing over time. The process of detecting salt deposits in space begins with understanding the light that reflects off planetary surfaces. Every substance, whether rock, ice, or mineral, interacts with light in its own special way. Salt, for example, has a unique signature that can be identified when light from the sun, or from a spacecraft's instruments, bounces off a planetary surface and is captured by highly sensitive sensors. Scientists call this method spectroscopy. By analysing the wavelengths of light that are absorbed or reflected, researchers can determine what molecules are present. This is not a simple task, because the signals from distant worlds are faint, and they are often mixed with signals from other materials. Yet, with patient observation and advanced technology, it becomes possible to isolate the patterns that indicate the presence of salts, such as sodium chloride, magnesium sulfate, or even more exotic chemical compounds. One of the most famous examples of salt detection beyond Earth comes from one of Jupiter's moons, Europa. Europa is an icy world, slightly smaller than Earth's moon, and it has long fascinated scientists because beneath its thick frozen surface there may lie a vast ocean of liquid water. The possibility of such an ocean is thrilling because water is the essential ingredient for life as we know it. For decades, astronomers and planetary scientists have studied Europa through telescopes on Earth, spacecraft flybys, and now, more recently, through the remarkable eyes of the James Webb Space Telescope. When scientists examined the surface of Europa, they noticed areas that reflected sunlight in ways that were unusual, shimmering with a brightness and spectral signature that hinted at the presence of salt. These salts are believed to have come from the subsurface ocean, brought to the surface by cracks, fissures, or geysers that allow the hidden water to seep upward, freeze, and deposit its dissolved minerals on the icy crust. This discovery is monumental because it tells us that Europa's ocean is not isolated but may interact with the surface, creating chemical cycles that could potentially support life. The story of salt detection is not limited to Europa, however. Similar discoveries have been made on Mars, our neighbouring planet, which has long been a target of human curiosity. Mars today is a cold and dry world, but evidence shows that in the past, water flowed across its surface, forming rivers, lakes, and possibly even oceans. When rovers such as Spirit, Opportunity, and Curiosity explored the Martian terrain, they uncovered crusts of salt, sometimes called evaporates, left behind when water evaporated long ago. These salts provide a chemical diary of Mars' ancient climate, showing that the planet once had conditions that might have been favourable for microbial life. For example, in one region known as Meridiani Planum, Opportunity discovered large deposits of hematite and sulfates, both of which form in the presence of water and often include salts. These findings suggest that water was not only present, but may have been abundant enough to sustain chemical reactions necessary for life. By studying the type and concentration of salts, scientists can reconstruct the environmental conditions that existed billions of years ago, revealing whether the water was acidic, neutral, or salty, and how long it persisted. The detection of salts is not done just by looking at the ground. Spacecraft also use orbiting instruments to scan large areas from above, capturing subtle differences in reflected light across the surface. For example, spectrometers can detect specific infrared or ultraviolet wavelengths that are absorbed by salts. This allows scientists to map the distribution of salts across entire planetary bodies, giving a broader picture of their geology and history. On Europa, scientists have identified regions rich in sodium chloride, a familiar table salt, as well as areas containing magnesium and sulfate salts. These findings suggest that Europa's hidden ocean may interact with the rocky mantle beneath it, dissolving minerals and bringing them to the surface, where they crystallize as salt deposits. Such interactions are important because they hint at complex chemistry, one that could provide the energy and nutrients needed for life in the ocean below. Salt detection has also been extended to other icy moons in the outer solar system. For instance, Saturn's moon Enceladus has captured attention for its geysers, which spew water ice, salts, and organic compounds into space. By analysing the plumes, scientists discovered sodium salts, confirming that a liquid ocean exists beneath the icy crust. The presence of salts in the plumes is significant because it suggests that the ocean interacts with the rocky core of the moon, just like Europa, and that this interaction could create chemical gradients necessary for life. Even in such distant worlds, salts act as markers of dynamic processes, providing a window into hidden oceans and potential habitability. Detecting salts is also crucial for understanding the possibility of life beyond Earth. On our planet, salty environments such as oceans, salt lakes, and hydrothermal vents are home to diverse microbial communities. Salt, while sometimes challenging for life to tolerate, also provides essential ions that are critical for cellular functions. When scientists find salt deposits on other worlds, they gain clues about where water once existed and where life might have found a foothold. Moreover, certain types of salts can preserve organic molecules, protecting them from radiation or degradation over millions or billions of years. This makes salt-rich areas prime targets for future missions searching for signs of life, whether past or present. The detection of salts is often a painstaking and delicate process. Instruments must be carefully calibrated, as even small errors can produce false signals. In addition, the surfaces of moons and planets are exposed to harsh conditions, including cosmic radiation and solar wind, which can alter or obscure chemical signatures. Scientists must account for these effects when interpreting their data, using models and laboratory experiments on Earth to simulate extraterrestrial conditions. For example, researchers study how salts behave under extremely low temperatures, under high radiation, or mixed with ice and dust, to understand how the signals they detect in space correspond to actual deposits. Historically, the recognition of salts in the solar system was gradual. Long before the age of sophisticated spacecraft, astronomers noticed unusual colours and brightness on the surfaces of distant moons, hinting at unusual chemistry. It was not until flybys and orbital missions that the nature of these materials became clear. In 1979, the Voyager 1 and Voyager 2 spacecraft provided the first detailed images of Jupiter's moons, revealing fractured ice and mysterious bright patches. Later, in the 1990s, the Galileo spacecraft orbited Jupiter and carried instruments capable of analysing surface compositions. Galileo's data showed clear evidence of salts on Europa, establishing a connection between the surface and a subsurface ocean. The accumulation of this data over decades has transformed our understanding of icy worlds from frozen, lifeless balls of ice to potentially vibrant, chemically active oceans waiting to be explored. The importance of salt detection is not just scientific but also practical for future exploration. As humans and robotic missions venture further into the solar system, knowing where salts and water are located could guide landing sites, resource use, and mission planning. On Mars, for instance, understanding the distribution of salts helps in selecting sites where water might be extracted, or where past life might have existed. On Europa and Enceladus, salts indicate regions where subsurface oceans might be accessed through cracks or plumes, guiding the design of instruments and landers capable of sampling these environments safely. Modern technology, especially telescopes like the James Webb Space Telescope, has revolutionized the ability to detect salts. Webb's powerful infrared instruments can peer through thin layers of ice and capture precise spectral signatures, revealing the presence of minerals that were previously invisible. For Europa, this means scientists can map salt deposits with unprecedented detail, observing variations across the surface and identifying areas where the subsurface ocean may be communicating with the ice above. This level of detail brings us closer than ever to understanding the chemistry, history, and potential habitability of distant moons. Even as we detect salts and study their distribution, questions remain. What is the composition of the oceans beneath these icy crusts? Are the salts mixed with other chemicals that could provide nutrients for life? How do geological processes bring the salts to the surface, and how frequently does this occur? Each discovery leads to new questions, driving further missions and studies. The excitement of salt detection lies not only in the confirmation of water-related chemistry, but in the broader story it tells about planetary evolution, the potential for life, and the dynamic processes shaping these alien worlds. The surface of Europa, one of Jupiter's most fascinating moons, has long intrigued scientists and astronomers. What captures the imagination most vividly are the intricate patterns of cracks, ridges, and grooves that stretch across its icy exterior. These surface features are not random. They tell a story of a world that is both dynamic and mysterious, hinting at the hidden activity beneath the frozen shell. When one gazes upon the images captured by spacecraft like Galileo and observes the detailed photographs from the Hubble Space Telescope, the surface of Europa appears as if it has been etched with countless lines and ridges, forming a vast network of fractures that crisscross the entire moon. Each of these features provides crucial evidence about the geological processes shaping this icy world, and, perhaps most importantly, about the ocean that lies hidden below its frozen crust. Europa's surface is primarily composed of water ice, which reflects sunlight strongly, giving the moon a bright, almost pearly appearance. Yet, despite its gleaming surface, the ice is far from uniform. Across vast stretches of the moon, there are long linear cracks, some of which extend for hundreds of miles, curving and intersecting in ways that resemble the intricate patterns of a spider's web. These cracks are often bordered by ridges, raised formations of ice that can tower several hundred feet above the surrounding terrain. The presence of these ridges suggests that the ice has been pushed up from below, possibly by a combination of tidal forces exerted by Jupiter's immense gravity and the movement of subsurface material. Scientists believe that these forces stretch and compress the ice as Europa orbits Jupiter, causing it to crack and shift in dramatic ways. The resulting landscape is one of constant change, where the ice is pulled, pushed, and reformed over millions of years. One of the most striking features observed on Europa's surface is a series of parallel ridges and bands, often called lineae. These dark streaks can span thousands of miles, sometimes crossing the entire hemisphere of the moon. The formation of these lineae is thought to be related to the movement of subsurface liquid water. Scientists hypothesize that warm water or slushy ice from below the surface occasionally rises through the cracks, refreezing as it reaches the colder exterior. This process leaves behind darker bands, which may be rich in salts or other minerals carried from the ocean beneath. The patterns of these ridges are not only visually captivating, but also scientifically valuable, providing clues about the interactions between the surface and the hidden ocean below. They are evidence that Europa is not a static, frozen world, but a dynamic one, where internal forces constantly shape and reshape the landscape. In addition to the linear cracks and ridges, Europa's surface displays a variety of other features that further point to internal activity. There are chaotic regions where the ice appears broken into blocks and slabs, jumbled together as if pushed and rotated in a massive icequake. These areas, sometimes spanning hundreds of miles, indicate that the ice shell is fractured and mobile, capable of shifting over time. The movement of these ice blocks may be driven by the tidal flexing caused by Jupiter's gravitational pull, which creates stress and tension in the crust. As the ice moves, it exposes fresh material from below, which may be a mixture of water, ice, and possibly salts, giving rise to the varied coloration seen on the surface. These chaotic regions are particularly important because they may represent areas where the icy shell is thinner, offering a potential window into the subsurface ocean. If future missions can target these regions, scientists may gain a more direct understanding of Europa's hidden seas. Another key aspect of the surface cracks and ridges is their orientation and distribution. Scientists have observed that many cracks align in specific directions, forming patterns that suggest global stresses acting on the moon's ice shell. For example, some fractures run predominantly from north to south, while others run east to west, intersecting and creating complex networks. The patterns of these cracks provide important insights into the forces at work within Europa. By studying the angles and intersections of these ridges, researchers can infer the locations and magnitudes of stress within the ice, offering a glimpse into the internal dynamics of the moon. These patterns also suggest that Europa's ice shell is not uniform in thickness, with some areas being thinner and more prone to cracking, while others remain more stable. This unevenness may be crucial for understanding how material from the subsurface ocean can reach the surface and interact with the icy crust. The ridges themselves vary widely in size and shape. Some are relatively small, rising just a few tens of feet above the surrounding ice, while others are enormous, towering several hundred feet and stretching for hundreds of miles. The width of these ridges also varies, with some only a few hundred feet across and others spanning several miles. Their appearance can be smooth or jagged, depending on the processes that formed them. In some cases, ridges appear to have been pushed up from below, forming symmetrical shapes on either side of a central crack. In other cases, they are more irregular, suggesting that they formed through the collision and displacement of ice blocks. These variations provide further evidence of the complex interplay between internal forces, tidal stresses, and surface interactions on Europa. One particularly fascinating feature associated with the cracks and ridges is the presence of double ridges. These are pairs of ridges separated by a trough or central valley, often a few hundred feet wide. Double ridges are thought to form when the ice is stretched and pulled apart, allowing material from below to rise and refreeze along the edges. The central trough may represent the area where the ice has pulled apart most dramatically, while the ridges on either side are the result of accumulated material or uplifted ice. These formations are especially interesting because they suggest that liquid or slushy water from beneath the ice may occasionally make its way to the surface, leaving behind visible signs of activity. In essence, double ridges may serve as windows into the processes occurring in the hidden ocean, offering tantalizing hints of a potentially habitable environment beneath the frozen shell. Scientists have also noted that many of the cracks on Europa appear to be relatively young in geological terms. Unlike impact craters, which can last for billions of years, the cracks and ridges show signs of ongoing activity and resurfacing. In some regions, newer cracks cut across older ridges, indicating that the surface is continuously changing and evolving. This ongoing activity suggests that Europa's interior remains warm and dynamic, possibly due to tidal heating caused by the gravitational tug of Jupiter and the neighbouring moons Io and Ganymede. The continuous formation of new cracks and ridges implies that the ice shell is not a rigid static layer, but a living, moving surface that responds to forces from within and from Jupiter's gravitational influence. This dynamic nature makes Europa one of the most intriguing bodies in the solar system for the search for extraterrestrial life, as it raises the possibility that liquid water, and perhaps the chemical ingredients for life, may be accessible beneath the surface. The chemical composition of the ridges and surrounding ice also adds to their scientific significance. Observations from spacecraft instruments have detected various salts, such as magnesium sulfate and sodium chloride, in the darker bands of the cracks and ridges. These salts are likely carried to the surface from the subsurface ocean, providing indirect evidence of its composition. The presence of these materials is important because it suggests that the ocean beneath Europa's ice may be in contact with the rocky mantle below, allowing for chemical exchanges that could support life. The interaction between the ocean and the surface ice, revealed through the study of cracks and ridges, paints a picture of a moon that is not merely frozen and inert, but one with the potential for a rich and complex internal environment. In addition to salts, some ridges show evidence of reddish and brownish hues, possibly indicating the presence of organic compounds or other materials brought up from the ocean. The variations in colour across the surface are closely tied to the cracks and ridges, suggesting that the fractures act as conduits for material from the interior. This highlights the importance of detailed mapping and study of the surface features, as they may provide the most accessible clues about Europa's hidden ocean. The combination of physical formations and chemical signatures makes the study of cracks and ridges a central focus for missions aiming to explore the Moon in greater detail, such as NASA's Europa Clipper mission scheduled for launch in the mid-2020s. The scale of these features is truly breathtaking. Some cracks extend for more than 3,000 miles, nearly circling the Moon, which has a diameter of about 1,900 miles. This means that a single fracture can span more than 1.5 times the width of the continental United States. The enormity of these features underscores the immense forces at play within Europa, and the dramatic impact they have on the Moon's landscape. It also highlights the challenges faced by scientists in interpreting the processes that form these structures, as they must consider both local and global stresses, interactions between the ice and underlying ocean, and the effects of Jupiter's powerful gravitational pull. The study of surface cracks and ridges on Europa is not merely an academic pursuit. Understanding these features is essential for planning future missions that aim to land on the Moon or explore its subsurface ocean. Areas where the ice is fractured or thinner may offer safer landing sites or easier access to the ocean below. They may also be regions where chemical signs of life could be most readily detected. By mapping and analysing the patterns of cracks and ridges, scientists can prioritise targets for exploration and design instruments capable of probing the icy surface and the secrets it conceals. Each line, ridge and fracture is a clue, a fragment of a larger story about a moon that, beneath its frozen exterior, may harbour one of the most extraordinary oceans in the solar system. In the farthest, coldest reaches of our solar system, far beyond the swirling gas giants Jupiter and Saturn, drifts the mysterious windswept world of Neptune. This distant planet is a place of extremes, where icy gases and wild storms dance across the atmosphere in ways that have both fascinated and baffled astronomers for decades. Among its strangest and most striking features are enormous, shadowy storms known as Great Dark Spots, massive whirlpools of wind and cloud that rival the famous Great Red Spot of Jupiter. Though unlike Jupiter's enduring storm, Neptune's dark tempests are fleeting and ever-changing, appearing and disappearing over mere years instead of centuries. The most famous of these storms is called GDS 89, which is short for Great Dark Spot 1989. Humanity first laid eyes on it in the year 1989 when NASA's Voyager 2 spacecraft sailed past Neptune on its historic journey through the outer solar system. This encounter gave the world its first glimpse of a storm of this size and complexity on a planet so distant that sunlight takes nearly 4 hours to reach it from Earth. The sight was breathtaking. A dark, elongated oval swirling with immense energy, suspended in the icy blue atmosphere far from the warmth of the sun. Neptune's great dark spots are what scientists call anticyclonic storms. This means that the winds inside them swirl in the opposite direction to smaller cyclones, creating massive self-contained whirlpools of energy. Yet despite this similarity to Jupiter's Great Red Spot, Neptune's storms behave in a surprisingly different way. Inside these dark storms there are far fewer clouds than one might expect. Rather than persisting for centuries, as Jupiter's storm does, they usually appear for only a few years, fading or changing shape before they can age into anything permanent. From Voyager 2's observations and later studies using the Hubble Space Telescope, astronomers estimate that Neptune spends a little more than half of its time hosting one of these enormous dark tempests somewhere in its atmosphere. The Great Dark Spot of 1989 appeared in Neptune's southern hemisphere, stretching in a long oval shape approximately 13,000 kilometers from end to end and about 6,600 kilometers across, nearly the same size as our entire planet Earth. Its shape and appearance was strikingly similar to Jupiter's Great Red Spot, yet this Neptunian storm had a unique trait. It could drift slowly north or south over time, moving across the planet in ways that revealed the complex dynamics of Neptune's upper atmosphere. At the edges of the storm, Voyager 2 recorded winds racing at incredible speeds of up to 2,100 kilometers per hour, roughly 1,300 miles per hour, the fastest winds ever measured anywhere in the solar system. Many scientists believe that the Great Dark Spot was not a solid formation, but rather a gap in Neptune's upper methane cloud layer, allowing a glimpse of the darker, deeper layers below. Over the months and years, the storm's size and shape shifted dramatically, demonstrating the restless energy of the Neptunian atmosphere. Around the storm, bright white clouds appeared above the tropopause layer, shimmering like Earth's thin, wispy cirrus clouds. Unlike cirrus clouds on Earth, which are made of tiny water ice crystals and fade within hours, Neptune's clouds were composed of frozen methane crystals and floated 50 to 100 kilometers above the main cloud deck. These methane clouds could linger for 36 hours, long enough for Neptune to rotate fully twice beneath them. Dark spots like GDS 89 typically form in the troposphere, lower than Neptune's bright upper clouds, and can last for months before fading. When Hubble attempted to photograph the original Great Dark Spot in November of 1994, it had vanished entirely. Astronomers theorized that it either dissipated completely or became obscured by new clouds. Interestingly, smaller companion clouds that had formed alongside the storm remained for some time, hinting that elements of the storm's circulation might survive even after its dark appearance disappeared. Scientists also observed that these storms often fade when they drift too close to Neptune's equator, where the Coriolis forces that help keep them spinning weaken and lose their grip. Voyager 2 also recorded a smaller storm in 1989 called Dark Spot 2, which had vanished entirely before 1994. Since that time, the Hubble Space Telescope has been the main tool for detecting Neptune's dark storms because it can observe the planet in blue light, where these features stand out most clearly. In 1994, a new storm emerged in Neptune's northern hemisphere called the Northern Great Dark Spot, but it disappeared sometime between 1998 and 2000. Another northern dark spot appeared in 1996, lasting until before 1998. Years later, in 2015, Hubble detected a southern dark spot that drifted toward Neptune's pole before fading in 2017. Then, in 2016, an almost identical storm to the original Great Dark Spot appeared in the northern hemisphere. This new northern Great Dark Spot persisted for several years, though astronomers are uncertain whether it still exists today, as Neptune's distant location limits our observations. In 2018, another dark storm emerged in Neptune's northern hemisphere. The first one Hubble had observed from its initial formation. Though smaller than the original Great Dark Spot seen by Voyager 2, it still measured an astonishing 7,400 kilometers across, wider than the entire Atlantic Ocean. In August of 2020, this storm unexpectedly reversed direction, halting its drift toward the equator, puzzling scientists and revealing yet again the complex and unpredictable nature of Neptune's winds. Around the same time, a smaller storm, affectionately nicknamed Dark Spot Jr., appeared nearby, spanning about 6,300 kilometers before eventually fading. Some astronomers believe that the birth of Dark Spot Jr. may have influenced the larger storm's sudden change in motion. Careful studies of Neptune storms, including the southern dark spot and the northern Great Dark Spot of 2018, indicate that they are often preceded by 2 to 3 years of increased cloud activity in the region. Their disappearance may occur when bright companion clouds drift into the center of the storm, obscuring it from view in blue light. Looking to the future, astronomers are eager to send spacecraft back to Neptune for a closer look. In 2021, NASA considered launching a mission called Trident to study Neptune and its large moon Triton, but ultimately chose to send 2 missions to Venus instead. Another concept known as Neptune Odyssey is a proposed flagship mission that could launch in the year 2033, with the aim of orbiting Neptune, studying its turbulent atmosphere, and exploring Triton in great detail. Even China's space agency has outlined plans for a nuclear-electric-powered mission to this icy, windswept world. Neptune, with its ever-changing storms and winds faster than any other in the solar system, remains one of the most captivating and mysterious worlds in our cosmic neighborhood. Its great dark spots, powerful fleeting tempests of shadow and wind, continue to intrigue astronomers, offering a glimpse into the restless energy and hidden secrets of the farthest planet in our solar system. Neptune's great dark spots may not last forever, but they are among the most breathtaking and mysterious storms in the entire solar system. These colossal tempests are fierce, fast, and endlessly changing, swirling through the cold, deep blue atmosphere of a planet more than 4 billion kilometers away from the comforting warmth of our Sun. Neptune is home to some of the strangest and most powerful storms ever observed, known as the Great Dark Spots. These are not mere shadows on a map. They are enormous, living storms, forming in areas where the air pressure is unusually high. On Earth, storms usually appear when the air pressure drops, so Neptune's storms are the opposite of what we expect. They twist and churn across the planet, massive spirals of wind and cloud that seem alive with energy. At the edges of these spinning giants, winds can roar at speeds of up to 1,300 miles per hour, so fast that they could carry you all the way around the Earth in less than a single day. Astronomers have observed at least 6 of these great dark spots so far. They seem to emerge from deep within Neptune's atmosphere, and there is a curious pattern. The darker the storm itself, the brighter and more dazzling the surrounding clouds of frozen methane appear. These spots are fleeting, appearing and disappearing over the years, yet they leave an unforgettable mark on the icy giant's swirling skies. But Neptune is not alone in its love of extreme weather. Saturn, the ringed giant, has its own monstrous storm, one that at first glance looks surprisingly familiar, almost like a hurricane or typhoon on Earth. It even has a central eye and spiraling bands of clouds, yet the scale is beyond anything we can imagine at home. The storm's eye alone can stretch as wide as 1,250 miles, large enough to engulf several countries at once. Around the edges, bright clouds race at speeds of 330 miles per hour, whipping across the planet in dazzling displays of motion. The strangest feature of Saturn's storm is its shape. It forms a perfect hexagon, a six-sided figure unlike anything on Earth. When astronomers first saw images of it, they had to check twice, convinced they were seeing a trick of the light. The hexagon's eye is nearly 20 times larger than any hurricane's eye ever recorded on our planet, and its winds are about 4 times faster than the most powerful storms we have ever witnessed. Even more puzzling, Saturn's atmosphere has very little water vapour, the essential ingredient that fuels storms on Earth, yet the hexagon has persisted for decades. Locked in place at the planet's north pole, it seems held by some invisible cosmic hand. Beyond the giants of our solar system, astronomers have discovered countless other strange worlds, often called super-Earths. These planets are heavier than Earth but smaller than the icy giants Uranus and Neptune. Some are solid rock, some are gas, and some a mix of both. They range in size from just twice as massive as our planet to as much as 10 times Earth's mass. Sadly, they're all far beyond our reach for now. Among these distant worlds, there are also mini-Neptunes, planets that could be gas dwarfs, ice giants, or huge rocky bodies, all unlike anything we have nearby. Yet in our own solar system, there is a ruler above all others, Jupiter. This colossal giant is the largest and heaviest planet orbiting the Sun, apart from the Sun itself. Its gravity is so strong it shapes the orbits of other planets, and sometimes even devours them. Around 4.5 billion years ago, when Jupiter was still young, a massive protoplanet roughly 10 times heavier than Earth, made of rock and ice, crashed into it. The collision was so violent it shattered Jupiter's core, mixing hydrogen and helium with heavier elements. Over time, those heavier elements sank toward the centre, forming the dense core we see today. If Jupiter has swallowed a planet once, it might have done so more than once, and may do so again in the distant future. Scientists think that in the early solar system, there were many more large planets than we see now. For example, the space near Mercury is empty today, but around many other stars, similar regions are packed with planets between the size of Earth and Neptune. During those chaotic early years, young stars were surrounded by swirling disks of gas and dust. From this material, planets began to grow, like sprouts pushing up from fertile soil. Rocky planets formed near the star where it was hot, while gas giants took shape farther out, where cold conditions allowed them to hold on to lighter gases. Back then, planets' orbits were far from tidy. Some swung dangerously close to the Sun before drifting outward again, pulled and pushed by the gravity of other worlds. One fascinating idea, called the Grand Tack theory, imagines Jupiter as the ultimate cosmic disruptor. In its first few million years, Jupiter may have moved inward toward the Sun, like a ship tacking toward a buoy, only to turn and drift back outward. On its journey, it swept up enormous clouds of debris, colliding with forming planets and drastically altering their paths. When Saturn appeared, some of the chaos calmed, but the damage, or the transformation, had already been done. Jupiter may even have played a role in forming Earth's oceans. Its massive gravity can capture and redirect asteroids, flinging some into interstellar space while sending others hurtling toward the inner planets. Around 66 million years ago, a giant space rock struck Earth near what is now the Yucatan Peninsula in Mexico, triggering massive earthquakes, volcanic eruptions, towering tsunamis, and a mass extinction that wiped out the dinosaurs. The rock's origin remains uncertain. It might have been a wandering asteroid or a comet nudged from the far reaches of the Oort cloud by Jupiter's gravitational pull. In this way, the early solar system was like a colossal cosmic pinball machine, with Jupiter as the flipper, smashing comets and asteroids around the system. Some shattered under the Sun's tidal forces, sending fragments scattering through space. Ironically, it was in the aftermath of these violent collisions that our mammalian ancestors began to thrive. Without Jupiter's cosmic meddling, neither Earth as we know it nor life itself may have existed. Jupiter's role in shaping the solar system was far from gentle. It destroyed ancient worlds, cleared the way for smaller planets like ours, and may have both obliterated and delivered the ingredients for life. It is a planet of contradictions, destroyer and protector, predator and guardian. The solar system still dances to the rhythm of its enormous gravity. Jupiter might even be the reason we have yet to find the mysterious Planet 9, a hypothetical world thought to lie beyond Neptune's orbit, though not as far as Pluto. Our solar system can be imagined as three grand neighbourhoods. The first contains the inner planets, small rocky worlds like Mercury, Venus, Earth, and Mars. The second holds the outer planets, the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. And the third stretches into the farthest reaches, a distant frontier of strange and undiscovered worlds waiting to reveal their secrets. Planet 9, if it truly exists, might be about the same size as our Earth, or perhaps a little smaller, closer to the size of Mars. Long ago it may have wandered freely among the giant planets, the titanic gas worlds of our solar system, but these giants, with their immense gravitational pull, could not leave it alone. Eventually their powerful forces may have flung it far from its birthplace, sending it either to the frozen, shadowy outskirts of our solar system, or even out into the endless darkness of deep space, never to return. The idea that such a mysterious hidden world might be lurking unseen beyond Neptune adds a sense of wonder and suspense to our understanding of the cosmos. Now, let's turn to Jupiter, the largest planet in our solar system, and an object instantly recognizable from across the void because of its bold, colorful stripes. These stripes are not just for show, they tell a story about the planet's turbulent atmosphere. For a long time, scientists believed the stripes were shaped mainly by Jupiter's fierce winds and the swirling motions of gases in its thick layers. But now we know there is far more complexity at work. The pale, light-coloured stripes, called zones, are places where warm gas rises from deeper layers, climbing toward the cloud tops. In contrast, the darker bands, known as belts, are areas where cooler gas sinks downward. Even Jupiter's many moons may play a subtle role, tugging on its atmosphere with their gravity and nudging the giant planet's convection currents in intricate ways. The interplay of gases, temperatures and chemicals creates the stunning visual patterns that make Jupiter such a spectacle. Beneath these swirling clouds lies a mysterious, dense heart. Jupiter's core is not solid like Earth's, but instead a dense liquid mixture of helium and an exotic form of hydrogen called metallic hydrogen, along with heavier elements dissolved within. As you move outward from this core, the pressure and temperature gradually drop, and the liquid slowly transitions into the whirling, turbulent gases that make up the upper layers of the atmosphere. Scientists are not yet certain exactly how deep this liquid gas boundary lies, but it is believed that a few thousand miles below the cloud tops, Jupiter is almost entirely liquid. Even if you could peel away its thick, stormy blanket of gases, Jupiter would still dwarf many other planets, including its closest rival Saturn. Some astronomers have even nicknamed it a failed star. This label is not entirely accurate, but there is some truth behind it. Like real stars, Jupiter is made mostly of hydrogen. However, it is far too small to ignite the nuclear fusion reactions in its core that make stars like our Sun shine so brilliantly. In theory, any object can become a star if it gains enough mass. If Jupiter were to somehow accumulate enough extra material, the pressure and temperature at its core could rise until nuclear fusion began. To turn Jupiter into a star as bright as the Sun, it would need to be roughly 1,000 times more massive than it is today. Even to become a smaller, cooler star, a red dwarf, it would still require about 80 times its current mass. So, while Jupiter will never spontaneously light up like a star, it is fascinating to imagine how our solar system might have looked if it had somehow grown massive enough to do so. Such a star would have bathed the planets in intense radiation, making it much harder for worlds to form stable orbits, and for life to emerge anywhere in the system. Jupiter also holds another remarkable distinction. It spins faster than any other planet in our solar system. A single day on Jupiter lasts only about 10 hours, which is astounding when you consider that this planet is more than 300 times larger than Earth, and about 2.5 times as massive as all the other planets combined. Oddly enough, if Jupiter were to gain even more mass, it would not grow larger. Instead, it would become denser and shrink under its own gravity. Even if it were 4 times more massive than it is now, its size would remain roughly the same. Leaving Jupiter behind, we turn to one of the most fascinating worlds in the search for alien life, Enceladus, a tiny icy moon of Saturn. This small world hides a vast hidden ocean beneath its frozen surface. Recently, scientists discovered something extraordinary in that secret sea: phosphorus, the rarest of the 6 chemical elements essential for life. On Earth, phosphorus is vital for making soil fertile. But in the icy ocean of Enceladus, its concentration may be between 100 and 1,000 times greater than in our planet's oceans. This could be because the moon's ocean is rich in carbonates, minerals that behave a bit like fizzy soda water, dissolving phosphates from the rocky seabed and enriching the water with this crucial element. The discovery suggests that other icy moons around Saturn, such as Titan, could also have waters rich in phosphorus. This is thrilling for scientists because phosphates, compounds containing phosphorus, are essential for DNA, RNA, and the protective membranes that surround cells. Among the 6 elements necessary for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, phosphorus is the rarest. Finding it in such abundance makes Enceladus one of the most promising places to search for life beyond Earth. In 2004, the Cassini spacecraft made a daring journey through the faint dusty veil of Saturn's second outermost ring, the E-ring. Unlike ordinary dust, this ring sparkles with countless tiny grains of ice, constantly ejected from geysers on Enceladus. Cassini's cosmic dust analyzer examined these icy particles in exquisite detail and made a stunning discovery: the presence of phosphorus, the vital element for life as we know it. Even though Enceladus is Saturn's 6th largest moon, it is still small, measuring only about 314 miles across. To put that in perspective, the moon could fit entirely inside the US state of Arizona. When Cassini first approached Saturn, astronomers thought Enceladus was just a frozen, lifeless snowball drifting through space. But the discovery of plumes of water vapor and icy particles shooting from cracks in its surface told a completely different story. Beneath the frozen shell lies a vast global ocean, sandwiched between the icy crust and a rocky core. Earlier studies had already hinted that this hidden ocean might contain complex organic molecules, the very building blocks of life. Until now, scientists assumed phosphorus would remain trapped deep inside the moon's rock and never reach the ocean. The discovery turned that assumption on its head. By studying 305 ice grains from Saturn's E-ring, researchers found that 9 contained phosphates. This detection was clear and undeniable. Phosphorus is crucial for DNA, cell membranes, and energy transfer in living organisms. Its presence on Enceladus is certain, unlike other claims elsewhere in the solar system, such as the controversial reports of phosphine in Venus's clouds. Enceladus is not the only icy world that excites astronomers. Jupiter's moon, Europa, has long been considered one of the most promising places to search for extraterrestrial life. Beneath its icy shell lies a massive ocean of salt water, possibly between 40 and 100 miles deep. This ocean is buried under a thick layer of ice, roughly 10 to 20 miles thick, but cracks on Europa's surface sometimes vent plumes of water into space, much like the geysers on Enceladus. These plumes could carry chemicals from the hidden ocean, allowing future spacecraft to taste the water without drilling through miles of ice. Even more tantalizing, there may be shallower pockets of liquid water just below the surface, perhaps less than 1 mile down, dramatically increasing the chances of finding life and making exploration easier. The discoveries of these moons, Enceladus and Europa, remind us that the solar system is filled with wonders and secrets, hidden beneath layers of ice and gas. Each revelation brings us closer to understanding where life might exist beyond Earth, and how our cosmic neighborhood continues to surprise us with its beauty, mystery, and potential. Then there is Titan, the largest moon of Saturn, a world that is both strange and endlessly fascinating, yet in some ways eerily familiar to Earth. Titan is smaller than our planet and has gentler gravity, but its thick, hazy atmosphere is dominated by nitrogen, just as our own air is. What makes it even more extraordinary is that Titan is the only other place in the entire solar system where liquid actually flows on the surface. But there is a twist. The lakes and rivers here are not filled with water. Instead, they brim with liquid hydrocarbons, like methane and ethane, creating alien seas of golden and orange tones that glimmer under the distant sun. Beneath this enigmatic frozen landscape lies yet another mystery, a hidden vast ocean of liquid water beneath the icy crust. Scientists do not yet know whether this subterranean ocean reaches all the way down to the rocky layer beneath the ice. If it does, chemical reactions at that boundary could provide energy for life, just as they do on Earth's deep ocean floors, where life thrives in complete darkness around hydrothermal vents. The quest for life, of course, is not confined to icy moons. In the year 2003, the European Space Agency sent its Mars Express spacecraft to orbit the red planet, and it detected methane in Mars' thin, tenuous atmosphere. On Earth, most methane is produced by living things, from tiny microbes to cows digesting grass. But Mars offered a puzzle. Methane should remain in the atmosphere for roughly 300 years, yet by 2006 almost all of it had vanished, disappearing about 600 times faster than scientists had anticipated. The question remains, what or who made it, and where did it go? Mars hides another tantalizing secret beneath its rusty surface, the possibility that ancient microbes might still be alive, lying dormant underground. Deep beneath the surface, these microorganisms would be shielded from deadly cosmic radiation, allowing them to survive unimaginable stretches of time. Laboratory experiments simulating Martian conditions have shown that certain bacteria could endure for as long as 280 million years in such a protective underground environment. This means that if life ever arose on Mars, its traces could still be preserved, locked away beneath layers of ice and rock, waiting for us to uncover them. Today, the surface of Mars is a barren, cold and dry desert. Temperatures plunge so low that the ground is as frigid as dry ice, and any living cells left exposed there would quickly freeze and desiccate. Yet far below, in pockets of briny water or frozen soil, the ancient record of life might still exist, patiently lying in wait for explorers to reach it. If we scour every corner of our solar system and still find no life, humanity's hope extends far beyond to distant worlds called exoplanets, planets orbiting stars far beyond our own sun. Some of these faraway planets appear surprisingly promising. The closest known exoplanet to Earth is Proxima Centauri b. In cosmic terms, it is almost our next-door neighbour, located just 4 2/10 light-years away. Astronomers have discovered something remarkable about it. Proxima Centauri b may be more Earth-like than first imagined. Its mass is only about 17% greater than Earth's, making it similar in size and gravity. It orbits a star that is smaller, cooler and dimmer than our Sun, yet it sits in the star's habitable zone, the narrow range of distance where temperatures could allow liquid water to exist. However, this planet has peculiar quirks. It is likely tidally locked, meaning one side bakes in perpetual daylight while the other is trapped in endless night. Scientists are still uncertain whether it has any atmosphere at all. Proxima Centauri b orbits its star so closely that a full year, a complete orbit, takes only 11 Earth days. But this proximity has a cost. Powerful stellar radiation may be stripping away any air it once possessed. Without an atmosphere, liquid water could not survive on the surface, and life, as we know it, would find it extremely challenging to exist there. Another fascinating exoplanet is Gliese 832c, located 16 2/10 light-years from Earth, a short hop across the galaxy in cosmic terms. This super-Earth has roughly 5 times the mass of our own planet and orbits much closer to its small, cool red dwarf star, completing a year in just 36 Earth days. Because its star is dim and cool, Gliese 832c receives about the same amount of heat and light as Earth. Yet this planet may not be the friendly, life-bearing world we hope for. Scientists suspect that it could be cloaked in a dense, heavy atmosphere that triggers a runaway greenhouse effect, a process where the planet traps more heat than it can release, turning it into a scorching oven. If this is true, Gliese 832c would resemble Venus rather than Earth, with suffocating heat, crushing air pressure, and thick impenetrable clouds, rather than gentle skies and flowing rivers. Now imagine this. You're piloting a sleek galactic space cruiser through the vast darkness of space, heading to Outpost 52 to deliver vital supplies to its small scattered colony. Suddenly, warning alarms blare across your cockpit. You glance at the screens, but before you can identify the problem, something outside seizes your attention. The entire front of your ship is made from a transparent alloy, a one-way window to the cosmos, and through it you witness a sight both breathtaking and terrifying. A colossal wave of orange and purple plasma, sweeping toward you like a tidal wave of light. There is no time to analyze. You push the ship into its steepest dive, the alarms screaming louder, the hull shivering under immense strain. For a moment, you fear it may tear apart. But your vessel is fast and powerful. Against all odds, you slip beneath the roaring cloud just in time. As the plasma cloud surges past, glowing like a living storm, curiosity overtakes fear. You decide to follow. Your ship's computer begins scanning and analysing the phenomenon, and the results defy belief. This is no ordinary plasma storm. It is a galaxy wrecker. Back on Earth, when you were a young pilot in training, you studied the research of 21st century astronomers who puzzled over why some galaxies mysteriously stopped forming new stars, fading away before their time. They knew that stars are born in cold, dense clouds of gas. Over millions of years, gravity compresses these clouds until nuclear fusion ignites and brilliant new suns emerge. One of the most famous images from the Hubble Space Telescope, the legendary Pillars of Creation in the Eagle Nebula, captures such star nurseries where new suns are coming to life, but lurking in the shadows are forces that destroy these cradles of light. The entity you are chasing is one of them. A vast sweeping wave of plasma racing into young galaxies and stripping away the gas required to form new stars. It is like a cosmic broom, clearing away the raw materials of creation itself, choking off the birth of entire stellar generations. The result is the premature death of galaxies, snuffed out before they can even grow old, a dramatic reminder that the universe is both a place of wonder and ruthless destruction. In the ordinary universe we live in, hydrogen is the lightest, most unassuming element of all. It's the featherweight champion of matter, almost like the delicate whisper of the cosmos. On Earth, hydrogen floats freely in the air, hiding quietly in water, almost invisible to the human eye, yet essential for life itself. But when we shift our gaze toward the immense and mysterious planet of Jupiter, this seemingly simple element transforms into something extraordinary and almost unimaginable. Jupiter is unlike anything on Earth. It is a colossal world, so massive that it could fit more than 1,000 Earths inside it, and its sheer size brings with it pressures that defy everyday comprehension. The hydrogen there, normally airy and light, is crushed under forces that are more than 400 million times stronger than the air pressure we experience on the surface of our planet. To imagine it, consider the gentle touch of a breeze you might feel on a spring afternoon in your backyard. Now, multiply that invisible pressure by 400 million. That is the suffocating, overwhelming force that hydrogen must endure deep within Jupiter. Under such unimaginable compression, hydrogen stops being the soft, light gas we know and becomes something utterly alien, a shimmering, silvery liquid metal. Metallic hydrogen gleams like a liquid mirror, a substance so exotic that it seems more like the dream of a science fiction writer than a reality of our own solar system. But this isn't just a curiosity, it is a potential powerhouse of energy. In theory, metallic hydrogen could release up to 20 times more energy than the burning of the normal hydrogen. Imagine carrying a small vial of it in your hand with a single match. A flick could unleash a spectacular eruption of energy, a small demonstration of forces so powerful they could rival nature itself. Yet, before anyone can entertain the wild idea of lighting fires on Jupiter, the first problem emerges: getting there. While Jupiter is only one planet further from the Sun than Mars, it might as well be 1,000,000 light-years away in terms of the journey. Between Mars and Jupiter lies the asteroid belt, a vast, chaotic field of rocky debris strewn across space like an endless cosmic minefield. These space rocks are not small pebbles. Many are enormous, measuring distances comparable to the span between Los Angeles and Las Vegas, while some are the size of entire states. The largest of them all, Ceres, is so vast that it is officially classified as a dwarf planet, nearly as wide as the state of Alaska. Any spaceship attempting to traverse this treacherous belt must thread a delicate path through a relentless storm of giant boulders, each one capable of obliterating it on impact. Even after surviving the perilous asteroid belt, the voyage to Jupiter is no simple jaunt. It would take roughly 650 days, nearly 2 full years spent inside the confined, artificial environment of a spacecraft. To put that in perspective, the longest single mission humans have ever endured in space lasted only 84 days. 2 years of artificial air, recycled water, and the endless hum of machinery would be required just to reach the giant planet. And that is before anyone even considers the challenges of living there. Suppose, however, that after 2 long years, you finally arrive at Jupiter. In your mind, you picture the thrilling scene. You strike a match, and in an instant, the hydrogen around you bursts into a spectacular flame, lighting the sky with unimaginable brilliance. But reality is far less forgiving. Jupiter's gravity is roughly 3 times stronger than Earth's, so your body feels heavier, every movement becomes sluggish, and your simple match seems to weigh more than a bowling ball. Attempting to leap or even move quickly is nearly impossible, and then comes the most fundamental obstacle. Jupiter has no solid surface. It is a gas giant, a planet of swirling clouds and thick, crushing atmospheres. Any attempt to land would be futile. You would sink endlessly into a layered world of gases, growing denser and denser until the very hydrogen itself turns into exotic liquids under the immense pressures. Only in the upper layers of Jupiter's atmosphere might you find lighter gases such as methane, seemingly perfect for igniting a flame. You strike a match, nothing. You strike again, still nothing. You even take out a portable burner, cranking it to maximum, yet the outcome is the same. The reason is simple. Fire requires 3 things to exist: fuel, an ignition source, and oxygen. Jupiter may have fuel in abundance, with methane and metallic hydrogen ready to unleash energy far beyond anything imaginable, and you have an ignition source in your match or burner. But it is missing the 3rd essential ingredient: oxygen. Without oxygen, combustion is impossible. Imagine lighting a small candle on Earth and covering it with a glass. The flame flickers and dies, leaving the wax untouched. Jupiter is the same principle, only on a planetary scale. Fire cannot breathe here, and without oxygen, it cannot exist. From our distant vantage point on Earth, we can observe countless meteorites, cast from the asteroid belt, plunging into Jupiter's atmosphere. They streak across the sky, burning brilliantly as friction ignites their outer layers, yet despite their small explosions, they never trigger a planetary inferno. Jupiter remains untouched, a testament to the scale and stability of this gaseous giant. If one were to attempt the impossible, to make Jupiter ignite, there is a terrifying method: initiating a thermonuclear chain reaction. But the logistics are horrifying. Even detonating every nuclear bomb on Earth would fall far short of the energy required. Jupiter is already bombarded by natural cosmic forces far more powerful than any human-made weapon. For instance, in the year 2009, a meteorite roughly the size of 5 soccer fields collided with Jupiter, unleashing an explosion equivalent to 5 billion tons of TNT. The impact left a dark scar on the planet's surface as wide as the Pacific Ocean. Even more dramatically, in the year 1994, fragments from the comet Shoemaker-Levy 202 slammed into Jupiter, leaving marks nearly as large as Earth itself, only for the planet's turbulent winds to erase them within weeks. The real challenge in destroying Jupiter, however, lies beneath the upper layers of clouds. The colossal metallic hydrogen stores are hidden deep within the planet, under pressures and temperatures that would instantly crush any human-made device. To truly ignite a chain reaction capable of tearing the planet apart, a force as massive as our moon would need to strike deep into the core, releasing energy on a scale so immense that Jupiter could disintegrate in seconds. The consequences of such destruction are almost beyond comprehension. Jupiter's obliteration would destabilize the solar system, shifting Earth's orbit and altering the rhythm of the sun in the sky. A shockwave from such a cataclysm could strip away the protective ozone layer, leaving our planet vulnerable to deadly solar radiation. The asteroid belt, once held in relative order by Jupiter's immense gravity, would scatter, sending rocks and meteors crashing toward Earth in endless bombardments. And perhaps most chillingly, there would be no one left to witness it. The explosion of Jupiter would resemble a miniature supernova, a brilliant and terrifying finale for a planet that is already a kind of failed star. If Jupiter were just 50 times more massive, it could ignite into a brown dwarf, a small, dim star. But as it stands, it remains the mighty gas giant, commanding the outer reaches of the solar system with silent authority. Given these realities, perhaps the wisest choice is not to play with planetary forces, but to observe and admire from afar. Jupiter's majesty does not require ignition to inspire awe, and if curiosity and adventure still beckon, one might look towards Saturn, a similarly vast and beautiful gas giant. Saturn's atmosphere, composed mainly of swirling hydrogen, helium and methane, presents the same challenge as Jupiter. No oxygen, no fire. Even the most extravagant supply of matches or the most sophisticated flame device would fail to produce a spark. But what Saturn does offer is a spectacle unlike any other. Its radiant, shimmering rings, stretching across space in arcs of icy brilliance, captivating any observer lucky enough to behold them. The ring's gentle glow and the planet's swirling clouds remind us that the universe's wonders are not always about explosive energy, but about subtle beauty and incomprehensible scale. In contemplating these giants, one comes to understand the true nature of our solar system. Hydrogen, the simplest and lightest element, can become a metallic marvel under the immense weight of a world more massive than imagination can easily hold. Meteors that are obliterated before they touch the surface of these planets demonstrate both the power and the restraint of cosmic forces, and the very idea of lighting a fire on a world without oxygen teaches us humility. Jupiter and Saturn exist as monumental signs of the vastness, the power, and the intricate balance of our solar system. Their gravity, their storms, their hidden metallic hydrogen, and their radiant rings all weave together a story of matter and energy on a scale so massive it dwarfs our human imagination. And while the fantasy of striking a match and igniting a world is a tantalizing one, the reality teaches us a deeper lesson. Some things are meant to be observed, marveled at, and respected from afar. The universe is a realm where sheer size, pressure, and elemental transformation create a theatre of unimaginable wonder, a place where hydrogen, the lightest of elements, can become liquid metal, where meteors burn but planets remain intact, and where beauty and danger coexist in a cosmic dance beyond anything Earth can contain. Uranus and Neptune are a different story. They are much smaller than Jupiter and Saturn, and they don't have metallic hydrogen deep inside them, so even if they could explode, the blast would not be as strong. But again, they have the same oxygen problem, no air you can breathe and certainly no atmosphere you can set on fire. Yet, there is one special planet where a match might actually work. Its name is GJ 1132b, and it is about 39 light-years away. Scientists think it might have oxygen in its air. It's not a huge gas planet, but a rocky world where you could, in theory, sit on the ground, strike a match, and watch a small fire dance as you enjoy an alien sunset unlike anything on Earth. Now, picture something very different. A frozen, ancient world. It has been around for about 4.5 billion years, barely warmed by the weak light of the faraway sun. Its surface is covered by a thick layer of ice. This world is smaller than our moon, yet a little larger than Pluto. Its name is Europa, the 6th moon of Jupiter, and one of the biggest moons in the whole solar system. And here is the most amazing thing about Europa. It might have life. Astronomers think it is one of the best places in the solar system to look for living things. Why? Because under that ice is a huge saltwater ocean, maybe between 40 and 100 miles deep. The ocean is hidden under an ice shell that could be 10 to 20 miles thick, but it might still be able to support life. Sometimes water jets burst through cracks in the ice, spraying parts of the ocean into space. That means some of Europa's secrets could be floating just above the surface, waiting to be studied by a passing spacecraft. Of course, getting down to that deep ocean would be very hard. But here's the exciting part. Scientists think there may be smaller pools of liquid water just below the surface, maybe less than a mile down. That would make it much easier for future missions to explore and look for signs of life. This idea came about by chance. Riley Coburg, the scientist leading the study, happened to see a colleague's presentation showing pictures of double ridges on Europa's icy crust. Coburg immediately recognized something familiar. He had seen ridges just like these on Earth. On our planet, these features are rare, but on Europa, they are everywhere. On Earth, double ridges form when water inside ice melts and then freezes again under high pressure, pushing the ice upward in two parallel peaks. If the same thing happens on Europa, it would be strong proof that shallow liquid water exists there. We still don't know how the ice acts in Europa's special environment, where the temperature, pressure and chemistry are very different from Earth's. We can't yet measure exactly how deep or large these pockets of water might be, or how long they stay liquid before freezing again. But one thing seems fairly clear. Water under the ice would be protected from Jupiter's strong radiation, which makes the chance of a life there even higher. Europa's ocean seems to be salty too. The reddish streaks on its surface might get their colour from strange frozen mixes of water and salts, different from anything on Earth. The yellow patches, on the other hand, could come from ordinary table salt, sodium chloride. In lab experiments, scientists recreated Europa-like conditions with water, salt, extreme cold, and high pressure, making a new kind of solid crystal. This unusual material might exist both at the bottom of Europa's ocean and on its frozen surface. Many mysteries remain, but help is coming. Around the year 2030, NASA plans to send the Europa Clipper mission to do several close flybys and look for signs of life. The European Space Agency is also sending its JUICE mission, short for Jupiter Icy Moons Explorer, which will visit Europa in the next few years. Europa, however, is not the only possible home for life in our solar system. In the year 2003, the European Space Agency's Mars Express spacecraft found methane in Mars' thin air. On Earth, most methane comes from living things, even something as simple as cows digesting grass. Scientists found that methane stayed in Mars' air for about 300 years. Then, in the year 2006, it almost completely disappeared, vanishing 600 times faster than models had predicted. One of the most interesting mysteries about Mars is the idea that tiny life forms, microbes, might be hiding deep under its surface. If they are there, they could have avoided deadly space radiation for millions of years. To test this idea, scientists recreated Martian conditions inside a lab. The results shocked them. Certain bacteria could survive in those harsh conditions for up to 280 million years. This means that if life ever existed on Mars, there's a real chance we could still find traces of it underground. All we would need to do is drill deep into the Martian soil to search for these ancient survivors. Right now, there is no flowing water on the surface of Mars. Any living cell or spore there would quickly dry out. The temperature on the surface is extremely cold, similar to dry ice, turning the planet into a frozen desert. Even so, scientists think there could be as many as 6 types of tough bacteria or fungi living far below the surface. The strongest of them has been nicknamed Conan the Bacterium because it can survive conditions that would destroy almost anything else. Now, let's leave the red planet and move to a very different world, Venus. In the year 2020, scientists made an announcement that caused excitement. They had found something in Venus's thick, poisonous air that might hint at life, a chemical called phosphine. This was exciting because phosphine can sometimes be made by microbes. Phosphine is a gas made of 3 hydrogen atoms and 1 phosphorus atom. It is very poisonous to life that needs oxygen, like humans. On Earth, it is usually found in places with little or no oxygen, like marshes and swamps where special bacteria make it. It can also be made in factories. Here's the strange part. Phosphine should not exist in Venus's air at all. The gas needs very specific conditions to form, like high pressure, the right temperature and lots of hydrogen. You might expect to find it on big gas planets like Jupiter or Saturn, but on Venus, totally unexpected. Small amounts could be made during volcanoes, lightning storms, or when meteorites hit the planet, but not enough to match what scientists thought they had seen. This mystery made some researchers imagine alien microbes floating high above Venus's surface. But even if such life existed, how could it survive there? On Earth, some microbes can live in water with an acidity of about 5%, but that's their limit. Venus's clouds are over 90% sulfuric acid, much more deadly. The air is also 50 times drier than the driest desert on Earth. Then, in the year 2022, with better telescopes, Scientists decided that there was either no phosphine at all or just a tiny trace, so the search for life goes on, this time farther from Earth. Let's move to Jupiter, the giant of our solar system. This planet is so big that it is 318 times heavier than Earth and more than 2.5 times heavier than all the other planets combined. Here's a strange fact. If Jupiter somehow got more massive, it would actually shrink. That's because the extra weight would squeeze it tighter, making it denser without getting bigger. Scientists think Jupiter could have up to 4 times its current mass and still be the same size. Jupiter also spins faster than any other planet. It takes only 10 hours to make a full turn on its axis, and it gets hit by space rocks more often than anywhere else. Amateur astronomers have seen strange flashes in Jupiter's clouds, signs of big impacts. One famous collision happened in 1994, when a comet called Shoemaker-Levy 9 broke apart and crashed into Jupiter. The original comet was about the size of the asteroid that wiped out the dinosaurs on Earth, but before it hit, it split into more than 20 pieces. These impacts left dark marks on Jupiter's clouds that lasted for months. 15 years later, in 2009, astronomers saw a black mark the size of Earth on Jupiter. It was left by an asteroid about 650 to 660 feet long. For comparison, the biggest asteroid known to hit Earth struck Tunguska, Russia, in 1908. It caused a huge explosion, even though no crater was found. Two of the most remarkable phenomena in this alien world are the presence of sulfuric acid and the enormous radiation environment, both of which contribute to Jupiter's complex and dangerous nature. These features are not just scientific curiosities, they give us insight into the workings of the largest planet in our neighbourhood and the challenges any probe or future exploration might face. Sulfuric acid, a highly corrosive and reactive chemical, is found in Jupiter's atmosphere in surprising quantities. On Earth, sulfuric acid is well known as a component of acid rain, produced when sulfur dioxide gas combines with water in the atmosphere. On Jupiter, however, sulfuric acid behaves differently. The gas giant is mostly made up of hydrogen and helium, but it also contains traces of other elements and compounds, including sulfur compounds such as hydrogen sulfide. These sulfur compounds can be transformed into sulfuric acid by a combination of ultraviolet radiation from the sun and the planet's own complex chemical reactions high in the atmosphere. The result is an environment where clouds are not only made of ammonia, ice and water, as one might expect, but also contain droplets of concentrated sulfuric acid. These clouds are not gentle, fluffy or inviting. They're incredibly corrosive, capable of destroying most metals and organic matter on contact. The sulfuric acid clouds in Jupiter are found primarily in the upper layers of the atmosphere, where sunlight is still able to penetrate and provide the energy needed to drive chemical reactions. As the sulfur compounds are exposed to ultraviolet radiation, they are broken apart and recombined, forming new molecules including sulfuric acid. These acid droplets can collect into clouds, producing storms that are both chemically and physically violent. Imagine a storm on Earth, such as a hurricane or a typhoon, but instead of rain and wind, it contains droplets of liquid sulfuric acid being hurled at tremendous speeds. The very idea is almost unimaginable, yet this is the reality on Jupiter. Any spacecraft attempting to penetrate these clouds would face an enormous challenge, as sulfuric acid is capable of corroding metal surfaces, damaging sensors, and interfering with electronic instruments. But sulfuric acid is only part of the story. Jupiter is also home to one of the most intense radiation environments in the entire solar system. The planet generates a powerful magnetic field that is more than 14 times stronger than Earth's. This magnetic field traps charged particles, electrons, protons, and heavier atomic nuclei, creating radiation belts that surround the planet. These belts are similar to Earth's Van Allen belts, but on a scale that is many thousands of times stronger. In fact, the radiation near Jupiter is so intense that it would be lethal to humans within minutes and can destroy the delicate electronics of spacecraft if they are not specially shielded. The combined effects of sulfuric acid and radiation make Jupiter a place of incredible danger and complexity, presenting significant obstacles to exploration. The interaction between sulfuric acid and radiation adds another layer of mystery and danger to Jupiter's environment. The radiation present in the planet's magnetic field is strong enough to break chemical bonds, creating reactive ions and radicals in the clouds of sulfuric acid. These highly reactive molecules can drive further chemical reactions, producing new compounds and altering the atmosphere in ways that are still not fully understood. The process is continuous. As sulfuric acid forms in the upper atmosphere, it is bombarded by intense radiation, leading to further breakdown and recombination of molecules. This creates a dynamic and ever-changing chemical environment, where clouds are not static but constantly being modified by the powerful forces at work. Jupiter's radiation environment is not uniform. The strongest radiation is found near the equator, where the magnetic field is the most concentrated. Here, the radiation is so intense that any spacecraft must rely on heavy shielding to survive even for a short period. The famous Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided direct measurements of this radiation, revealing levels that were hundreds of times stronger than those found in Earth orbit. Instruments on the spacecraft were damaged over time, a testament to the harsh conditions present in the planet's vicinity. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, JUICE, and NASA's Europa Clipper, must also contend with this extreme environment, designing their spacecraft with materials and technologies capable of surviving both radiation and corrosive chemicals. One of the most fascinating aspects of Jupiter's sulfuric acid clouds is their role in the planet's dramatic weather systems. Jupiter is famous for its giant storms, including the Great Red Spot, which has raged for at least 350 years. Within these storms, sulfuric acid clouds are carried by powerful winds, mixing with ammonia and water clouds, producing a layered and chemically complex atmosphere. These interactions can influence the color and dynamics of the storms, creating bands, swirls, and eddies that are visible even from Earth. The chemical activity driven by sulfuric acid and radiation may contribute to the distinctive reddish-brown hues of some regions of the planet, as different compounds reflect and absorb sunlight in unique ways. The effects of sulfuric acid and radiation are not confined to the upper atmosphere. They may also influence the deeper layers of the planet. Although Jupiter is mostly a gas giant, it has regions of increasing pressure and density as one moves closer to the core. Here, sulfuric acid may exist in exotic forms, possibly dissolved in liquid hydrogen or interacting with other chemicals under extreme pressure. The high-energy radiation penetrating these layers can trigger reactions that would be impossible under Earth-like conditions, potentially creating molecules that are completely alien to us. This makes Jupiter a natural laboratory for studying chemistry under extreme conditions, offering clues to the kinds of reactions that may occur elsewhere in the universe. Another intriguing consequence of Jupiter's sulfuric acid and radiation environment is its effect on the planet's moons. Jupiter has over 90 known moons, ranging from tiny asteroid-like bodies to the giant Galilean moons, Io, Europa, Ganymede, and Callisto. Io, the most volcanically active body in the solar system, is bombarded by sulfur compounds and radiation from Jupiter, which interact with its volcanic plumes and surface materials. Europa, with its icy shell and potential subsurface ocean, is also exposed to sulfuric acid deposits and radiation, which can penetrate its surface ice to some depth. These effects may have significant implications for the chemistry and habitability of these moons, influencing the possibility of life or the development of prebiotic molecules. The study of sulfuric acid and radiation on Jupiter also sheds light on the broader processes shaping gas giants. Sulfuric acid is not unique to Jupiter. It is found in the atmospheres of other planets and moons, including Venus, where it forms thick reflective clouds. By comparing Jupiter's sulfuric acid with that of other worlds, scientists can learn how planetary atmospheres evolve, how chemical cycles operate under different conditions, and how magnetic fields influence radiation and chemistry. Jupiter's extreme conditions serve as a benchmark, helping researchers understand the limits of planetary processes and the variety of environments that can exist in the universe. Despite the dangers posed by sulfuric acid and radiation, these phenomena also make Jupiter one of the most fascinating planets to study. The interplay of chemistry, physics, and magnetism creates a dynamic and ever-changing environment, filled with storms, chemical reactions, and energy flows that challenge our understanding of planetary science. Observations from Earth-based telescopes, the Hubble Space Telescope, and space missions have revealed only glimpses of this complex world, hinting at the richness of the processes occurring beneath the cloud tops. Each new measurement adds a piece to the puzzle, revealing the ways in which sulfuric acid and radiation shape the planet's atmosphere, influence its storms, and affect its moons. The challenges posed by Jupiter's sulfuric acid and radiation are not only scientific but also practical. Any spacecraft visiting the planet must be carefully designed to resist corrosion, shield sensitive instruments from radiation, and survive the turbulent atmospheric conditions. Engineers use special materials, coatings, and shielding techniques to protect spacecraft from the acidic droplets and high-energy particles. In addition, missions must carefully plan their trajectories to minimize exposure to the most intense radiation belts, sometimes relying on brief flybys or distant orbits rather than close approaches. These constraints make Jupiter one of the most difficult planets to explore, yet also one of the most rewarding, as each mission returns invaluable data about the giant planet's chemistry, magnetism, and dynamics. Sulfuric acid and radiation are also important for understanding the history and evolution of Jupiter. The presence of sulfuric acid indicates that sulfur compounds have been part of the planet's atmosphere for a long time, potentially delivered by volcanic activity, comet impacts, or primordial material from the early solar system. The radiation environment, shaped by Jupiter's massive magnetic field, provides clues to the planet's internal structure, including the movement of metallic hydrogen and the rotation of the core. Together, these factors reveal how Jupiter became the giant we see today, how it interacts with its moons, and how it influences the rest of the solar system. Looking to the future, the study of sulfuric acid and radiation on Jupiter will continue to be a major focus of planetary science. Upcoming missions, advanced telescopes, and innovative laboratory experiments will help scientists understand the precise chemistry of the clouds, the dynamics of storms, and the effects of radiation on atmospheric molecules. These studies will not only deepen our knowledge of Jupiter, but also provide insights into exoplanets, planets orbiting other stars that may have similar conditions. By understanding Jupiter, we learn about the potential for extreme chemistry and energetic environments elsewhere in the universe, broadening our view of what is possible in planetary systems. Beneath the icy, pale surface of Jupiter's moon Europa, there may be far more happening than meets the eye. Among all these distant celestial bodies, Europa stands out as one of the most intriguing and mysterious places in our entire solar system. Slightly smaller than our own moon, Europa has long fascinated astronomers, not only because of its smooth, glistening icy surface, but also because of the tantalizing possibility that hidden beneath that ice lies a vast ocean of liquid water. This alone would make Europa extraordinary, but what truly sends ripples of excitement through the scientific community are the hints by James Webb Telescope that water plumes, shooting from the moon's interior into space, might exist. If confirmed, these plumes could provide direct access to the ocean beneath without the need to drill through kilometers of ice, offering humanity a rare glimpse into the hidden depths of another world. The surface of Europa is striking and unlike most other moons in the solar system. When first observed through telescopes in the early 20th century, Europa appeared to be a smooth, almost featureless sphere. Later, with more powerful instruments and spacecraft flybys, scientists discovered that its surface is actually crisscrossed with long, dark streaks that seem to stretch for hundreds or even thousands of kilometers. These streaks are known as lineae, and they are believed to be cracks in the ice, created by stresses in the moon's outer shell. As Europa moves through its slightly elliptical orbit around Jupiter, the planet's immense gravity tugs at it, flexing its icy crust in a process called tidal heating. This stretching and squeezing generates heat within the moon, preventing the entire ocean from freezing solid and causing fractures in the ice above. These cracks may serve as pathways for liquid water to escape from below, potentially forming towering plumes that shoot hundreds of kilometers into space. The mere thought of water erupting from a frozen moon so far from the sun, where sunlight is weak and temperatures plunge to hundreds of degrees below zero, is astonishing, reminding us just how diverse and unexpected planetary bodies can be. Hints of these water plumes first emerged from observations made by the Hubble Space Telescope. Around the year 2012, scientists began noticing strange patterns of ultraviolet light near Europa's southern pole. At first, these signals puzzled researchers because they did not correspond to anything seen before. After careful study, some scientists suggested that the ultraviolet glows could be caused by plumes of water vapour erupting from Europa's interior and scattering sunlight in a way that produced these unusual emissions. The evidence was subtle but compelling. Unlike Jupiter's famous moon Io, which actively spews lava due to volcanic activity, Europa does not have visible eruptions. Instead, the hints of water plumes appear as faint and fleeting features that may only be visible for a few hours or days at a time, making them challenging to observe and study. Scientists used repeated observations to confirm that these features seem to recur in the same regions, particularly near areas of fractured ice, lending further support to the idea that Europa might be actively venting water from its hidden ocean. The possibility of water plumes on Europa is more than a curiosity. It has profound implications for our search for life beyond Earth. On our planet, where there is liquid water, there is almost always life, ranging from simple microbes to complex plants and animals. If Europa's ocean contains water, salts, and other chemical ingredients necessary for life, the plumes might carry traces of microbial life or organic molecules directly from the ocean to space. Imagine a spacecraft flying through one of these geysers, collecting samples of water and analysing its chemical composition without ever having to land or drill through ice. This could be humanity's first direct look at the chemistry of another ocean world, providing unprecedented insights into whether life might exist elsewhere in the solar system. Scientists are particularly interested in finding molecules such as amino acids, the building blocks of proteins, or more complex organic compounds that are essential for life as we know it. Even the detection of salts, sulfur compounds, or other minerals could reveal the geologic and chemical activity occurring deep within Europa's hidden seas, showing that the moon is far from a frozen, lifeless world. The idea of water plumes has been supported by computer models and simulations as well. Researchers have used sophisticated simulations to understand how water could rise through Europa's icy shell. These models suggest that warm pockets of water trapped beneath the ice could find cracks or thin regions in the ice, forcing water upward due to pressure differences. As it reaches the surface, the water could vaporize in the near vacuum of space, creating a visible plume of gas and tiny ice particles. This process may happen in bursts rather than as a steady flow, which aligns with the fleeting nature of the plumes observed by telescopes. In some simulations, the plumes can reach heights of up to 100 kilometers or more, high enough to be detected by instruments from orbit. By carefully studying the dynamics of these eruptions, scientists can estimate the thickness of Europa's ice shell, the depth of the ocean below, and the potential chemical composition of the water, all without breaking through the surface. Future missions to Europa are being designed with these plumes in mind. NASA's Europa Clipper, scheduled to launch in the early 2020s, will orbit Jupiter and perform dozens of close flybys of Europa. Equipped with advanced cameras, spectrometers, and particle detectors, Europa Clipper will search for signs of plumes, map the moon's surface in unprecedented detail, and analyze the composition of any water vapor it encounters. By flying directly through suspected plume regions, the spacecraft could sample material that has traveled from the ocean below, offering scientists a unique opportunity to study the moon's internal chemistry without drilling. This mission, along with potential future landers or even sample return missions, could finally answer the question that has captivated astronomers for decades: is there life hiding beneath Europa's icy shell? The anticipation is enormous, as Europa represents one of the best chances to discover life beyond Earth within our own solar system. Europa's water plumes are not only scientifically exciting, but also visually spectacular to imagine. Picture a vast, frozen landscape stretching across thousands of kilometers under a thin but extremely strong ice crust. From deep below, liquid water rises, sometimes breaking through the ice in towering jets that catch the weak sunlight of Jupiter's distant orbit. Fine droplets scatter light, forming fleeting halos or faint glows against the dark backdrop of space. If you could stand on Europa, assuming protective equipment to survive the extreme cold, you might see these plumes shooting hundreds of kilometers into the thin atmosphere. sparkling as they drift upward before freezing into tiny ice crystals that drift back down onto the icy surface. It is a scene that combines the elegance of delicate natural processes with the raw power of planetary forces, showing that even a small, cold moon can display phenomena as dramatic as Earth's most powerful geysers or volcanoes. The scientific, philosophical, and even human significance of these plumes is enormous. For centuries, humans have asked whether we are alone in the universe and whether life exists beyond our blue planet. Europa offers a tantalizing answer. If plumes are confirmed and found to contain the chemical ingredients of life, it could revolutionize our understanding of biology, planetary science, and our place in the cosmos. Europa's hidden ocean may have been stable for billions of years, providing a long-lived environment where life could potentially arise and evolve independently of Earth. This challenges the traditional view that life is rare and Earth-centric, instead suggesting that the universe may be filled with hidden pockets of habitable worlds, waiting to be discovered through the icy plumes of distant moons. The hints of water plumes from Europa's interior remind us that even in the outer reaches of the solar system, far from the warmth of the sun and the familiar conditions of our home planet, the forces of nature can create astonishingly dynamic environments. They show that icy moons are not mere barren balls of rock and frozen water, but active, evolving worlds with oceans, chemistry, and perhaps even biology hidden beneath their frozen shells. Europa, with its icy surface, fractured lineae, and mysterious plumes, stands as a symbol of human curiosity and the endless possibilities that await when we look beyond our own planet. The more we study it, the more it challenges our imagination, inspiring us to dream of the day when humanity might directly touch, explore, or sample the waters of a distant ocean world, uncovering secrets that have remained hidden for billions of years beneath the ice. Europa's potential water plumes are far more than an astronomical curiosity. They are a gateway to understanding one of the most compelling mysteries in planetary science, the possibility of a life beyond Earth. From the first subtle ultraviolet glows spotted by the Hubble Space Telescope in the year 2012 to the upcoming missions that may finally probe these jets of water, Europa continues to captivate and inspire. Its icy surface, cracks, and potential plumes form a dynamic system that is both beautiful and scientifically invaluable. By studying these plumes, humanity may gain unprecedented insight into the hidden ocean below, the chemistry of another world, and the potential for life beyond our planet, expanding our understanding of the universe in ways we are only beginning to imagine. Europa's secrets, locked beneath layers of ice for billions of years, may soon be revealed, offering a glimpse into the deep, cold, and mysterious waters of a distant alien world. The concept of a thermal hotspot refers to a region that is significantly warmer than its surroundings. On Earth, we are familiar with thermal hotspots in the form of volcanic regions, geysers, or areas with unusually high geothermal activity. On Jupiter, thermal hotspots are very different, not least because the planet lacks a solid crust. Instead, these are regions where the temperature in the planet's thick atmosphere rises unexpectedly, creating localized pockets of heat in a world otherwise dominated by extreme pressures, turbulent storms, and swirling clouds of gas. Scientists first began to suspect the existence of these hotspots through observations made using infrared astronomy, which allows us to detect heat patterns that are invisible to the naked eye. Unlike visible light, which can be scattered and absorbed by clouds, infrared radiation can reveal the actual thermal energy coming from deep within Jupiter's atmosphere. One of the first striking discoveries of Jupiter's thermal hotspots came from missions such as the Galileo spacecraft, which reached the planet in the year 1995, and the more recent observations by the Juno spacecraft, which entered Jupiter's orbit in the summer of 2016. These missions provided scientists with a detailed view of the planet's atmospheric layers, revealing that Jupiter is not a uniform sphere of gas but a dynamic and layered world, with regions of intense heat, powerful storms, and continuous motion that stretches thousands of kilometers across. Thermal hotspots, as it turns out, are closely linked to the planet's unique atmospheric composition and internal processes. Unlike Earth, where the sun is the primary source of heat, Jupiter generates a significant portion of its own internal heat. The interior of Jupiter is compressed under immense pressure, with the weight of the planet's thick atmosphere pressing down upon its deeper layers. This compression causes the hydrogen inside the planet to transition into a state called metallic hydrogen, a form of hydrogen that behaves like an electrically conductive metal. The creation of metallic hydrogen is not just a curiosity of physics, it is also a source of tremendous heat. As hydrogen atoms are squeezed together in the core, energy is released, radiating outward and contributing to the planet's overall warmth. In some places, this energy escapes more easily than in others, creating localized regions where temperatures are higher than in the surrounding atmosphere. These are the potential thermal hotspots of Jupiter, areas where heat is concentrated and where atmospheric dynamics become especially interesting. Infrared observations have revealed that Jupiter's thermal hotspots are often located in the equatorial region of the planet, although they can also appear in other latitudes. These hotspots are usually several hundred degrees hotter than the surrounding atmosphere. To give a sense of scale, the average temperature in the upper layers of Jupiter's atmosphere is around -140 degrees Celsius, or about -220 degrees Fahrenheit. In contrast, thermal hotspots can reach temperatures that are significantly warmer, sometimes tens of degrees higher, creating pockets of relative heat in an otherwise frigid environment. These temperature variations, although they may seem modest compared to the intense heat of stars, are extremely important for understanding the circulation patterns and chemical reactions occurring within Jupiter's atmosphere. One of the most intriguing aspects of these thermal hotspots is their connection to the planet's famous atmospheric features, such as the Great Red Spot, the planet's gigantic and centuries-old storm. While the Great Red Spot is primarily a visible phenomenon, the thermal hotspots reveal that there is far more happening beneath the surface of the clouds. Hotter regions can create rising currents of gas, which in turn affect wind patterns, storm formation, and the transport of chemical elements like ammonia, methane, and water vapor. In essence, these thermal hotspots act as engines that drive parts of Jupiter's atmospheric machinery, contributing to the planet's endlessly shifting weather and spectacular cloud patterns. The origin of these hotspots can be traced to several factors. One major factor is Jupiter's rapid rotation. The planet spins once approximately every 9 hours and 55 minutes, which is extremely fast given its enormous size. This rapid rotation creates powerful Coriolis forces that twist and stretch the planet's atmosphere into bands of alternating eastward and westward winds. Between these bands, the atmospheric pressure can vary dramatically, and in some of these low-pressure regions, heat from the interior can rise more easily, creating localized thermal hotspots. These regions are often observed as dark areas in infrared images, indicating that heat is escaping from deeper layers of the atmosphere. Another contributing factor is the presence of large-scale storms and vortices. Jupiter's atmosphere is in constant motion, with turbulent eddies, convective plumes, and swirling clouds that can span thousands of kilometers. When these storms interact with the deeper layers of the atmosphere, they can tap into the internal heat of the planet, bringing warmer gas upward. These convective upwellings can create temporary thermal hotspots, which may last for hours, days, or even longer. In some cases, these hotspots may migrate along the atmospheric bands, moving with the prevailing winds and merging with other regions of heat, producing even more complex patterns. Observations of thermal hotspots have also revealed fascinating details about the chemical composition of Jupiter's atmosphere. Hotter regions tend to have lower concentrations of certain compounds, such as ammonia, because the rising heat causes these molecules to break down or disperse. Conversely, other molecules, such as phosphine and hydrocarbons, are more abundant in these areas, providing clues about the chemical reactions taking place under extreme conditions. By studying the patterns of thermal hotspots, scientists can infer not only the temperature variations, but also the hidden chemistry of a planet that remains invisible in ordinary visible light. In this way, thermal hotspots serve as windows into Jupiter's deeper mysteries, revealing the planet's internal energy sources and the complex interactions of its gases. One particularly famous set of thermal hotspots is found near Jupiter's equator and is known as the 5-micron hotspots. These regions are so named because they emit strongly in the infrared light with a wavelength of about 5 micrometers. At this wavelength, the infrared radiation can escape from deep within the atmosphere, giving scientists a direct glimpse into layers that are otherwise hidden by thick clouds. The 5-micron hotspots are usually long and narrow, stretching thousands of kilometers in the east-west direction, while remaining relatively narrow in the north-south direction. These hotspots are not permanent. They drift slowly over time, influenced by Jupiter's complex wind patterns, but they remain remarkably consistent in shape and location, indicating that there is a stable underlying mechanism driving their formation. The study of these thermal hotspots has also shed light on the vertical structure of Jupiter's atmosphere. Unlike Earth, where atmospheric layers are relatively thin compared to the planet's radius, Jupiter's atmosphere extends for thousands of kilometers and gradually transitions into a dense fluid interior. Thermal hotspots often mark regions where warmer gases from deeper layers are able to rise closer to the visible cloud tops. By measuring the temperature and movement of these hotspots, scientists can estimate the depth of atmospheric convection, the rate of heat transport, and the energy output of the planet itself. In this sense, thermal hotspots are not merely localized curiosities, they are vital clues to understanding how Jupiter generates and redistributes energy across its immense bulk. It is also worth noting that these hotspots are not limited to the equator. Observations by the Juno spacecraft have revealed the presence of thermal anomalies in higher latitudes, including regions associated with Jupiter's polar cyclones. These polar cyclones are massive hurricane-like storms that cluster around the planet's poles, forming almost perfect geometric arrangements. The heat associated with these polar vortices suggests that thermal hotspots may exist at multiple levels of the atmosphere, from the deep interior to the upper cloud layers. This discovery challenges earlier models that assumed heat distribution on Jupiter was relatively uniform and highlights the dynamic and heterogeneous nature of the planet's atmospheric processes. Understanding Jupiter's thermal hotspots is not only important for studying the planet itself, but also for gaining insight into gas giants more generally. Other planets in our solar system, such as Saturn, Uranus, and Neptune, share some characteristics with Jupiter, including thick atmospheres, strong internal heat sources, and rapid rotation. By studying the thermal patterns on Jupiter, scientists can develop models that apply to other gas giants, both in our solar system and around distant stars. Thermal hotspots provide a natural laboratory for exploring the behavior of fluids under extreme pressures and temperatures, the interaction of atmospheric chemistry with heat transport, and the influence of rapid rotation on planetary weather systems. In many ways, Jupiter's hotspots are a gateway to understanding the fundamental physics of giant planets everywhere. The potential implications of thermal hotspots extend even further when considering the possibility of life in the outer solar system. While Jupiter itself is far too hostile for life as we know it, its moons, such as Europa and Ganymede, are influenced by the planet's heat and magnetic field. Thermal hotspots in Jupiter's atmosphere may play a role in the planet's overall energy budget, affecting the radiation environment, particle flux, and tidal heating experienced by its moons. For instance, Europa's subsurface ocean is thought to be kept liquid in part by tidal forces generated by its interaction with Jupiter's gravity. Understanding how heat moves through Jupiter itself can help refine models of how energy is distributed throughout the entire Jovian system, which in turn informs our search for habitable environments beyond Earth. In conclusion, potential thermal hotspots on Jupiter represent some of the most fascinating and mysterious aspects of this enormous gas giant. They are regions of concentrated heat, often hidden beneath thick clouds, that reveal the underlying energy, motion, and chemistry of the planet. From the equatorial 5-micron hotspots to the polar cyclones, these regions provide crucial clues about Jupiter's internal heat, atmospheric circulation, and chemical composition. They remind us that even a planet without a solid surface can be dynamic, complex, and endlessly surprising. As we continue to explore Jupiter through missions like Juno and future spacecraft, the study of thermal hotspots will remain a key window into the inner workings of the largest world in our solar system, offering insights not only into Jupiter itself, but into the nature of giant planets throughout the galaxy. The more we observe these hotspots, the more we realize that Jupiter is not merely a ball of gas, but a living, breathing system of energy, movement, and transformation, where heat rises and falls, storms swirl endlessly, and the invisible forces of pressure and rotation shape an ever-changing, ever-intriguing world. These potential thermal hotspots are far more than just warmer patches in the atmosphere. They are active players in the story of Jupiter, helping us understand how this immense planet maintains its remarkable energy, drives its spectacular weather, and interacts with its moons in ways that continue to challenge our understanding of planetary science. The James Webb Space Telescope, JWST, has provided groundbreaking insights into Jupiter's moon Europa, revealing compelling evidence of interactions between its subsurface ocean and icy surface. These findings significantly enhance our understanding of Europa's potential to support life and its dynamic geological processes. Europa, one of Jupiter's 4 Galilean moons, has long been a subject of scientific interest due to its smooth, icy surface and the possibility of a liquid water ocean beneath. Observations from previous missions, such as NASA's Galileo spacecraft, suggested the presence of a subsurface ocean, but direct evidence remained elusive. The JWST's advanced capabilities have now provided more detailed and convincing data supporting this hypothesis. One of the most significant discoveries made by the JWST is the identification of carbon dioxide on Europa's surface. Using its near-infrared camera, NIRCam, the telescope detected carbon dioxide in specific regions of the moon's icy crust. This carbon is believed to originate from Europa's subsurface ocean, rather than from external sources like meteorite impacts. The presence of carbon dioxide is particularly intriguing because carbon is a fundamental building block of life as we know it. The detection of this molecule suggests that Europa's ocean may have the necessary chemical ingredients to support life forms, if they exist. The distribution of carbon dioxide on Europa's surface also provides insights into the moon's geological activity. The JWST observations revealed that carbon dioxide is concentrated in areas known as Terra Regio, a region characterized by chaotic terrain and recent resurfacing. This pattern indicates that the carbon dioxide has been transported from the subsurface to the surface, possibly through cracks in the icy crust. Such processes imply that Europa's icy shell is dynamic and may be actively interacting with its underlying ocean. In addition to carbon dioxide, the JWST has detected other chemical compounds on Europa's surface, including hydrogen peroxide. These findings suggest that complex chemical reactions are occurring on the moon's icy crust, potentially driven by interactions between the surface and the subsurface ocean. The presence of these compounds raises intriguing questions about the chemical processes taking place on Europa and their implications for the moon's habitability. The evidence gathered by the JWST underscores the dynamic nature of Europa's ice ocean system. The interactions between the subsurface ocean and the icy crust are likely influenced by various factors, including tidal heating from Jupiter's gravitational pull and internal heat generated by radioactive decay. These processes may drive the movement of water and chemicals between the ocean and the surface, creating a complex and active environment. Understanding these interactions is crucial for assessing Europa's potential to support life. The exchange of materials between the ocean and the surface could provide essential nutrients and energy sources for any microbial life that might exist beneath the ice. Moreover, the chemical composition of the surface can offer clues about the conditions within the ocean, helping scientists determine whether it possesses the necessary elements and energy sources to sustain life. The JWST's observations have also revealed that Europa's surface ice is undergoing constant changes. The ice is crystallizing at different rates in various regions, indicating ongoing geological activity. These changes are particularly evident in areas like Terra Regio, where crystalline ice is found both on the surface and beneath it. Such dynamic processes suggest that Europa's icy shell is not static, but is instead subject to continuous modification, possibly due to interactions with the subsurface ocean. These findings have profound implications for future missions to Europa. The upcoming Europa Clipper mission, set to launch in the near future, aims to conduct detailed investigations of the moon's surface and subsurface. The data provided by the JWST will be invaluable in guiding the design and objectives of this mission, helping scientists prioritize areas of interest and refine their hypotheses about Europa's potential to harbour life. Jupiter, the giant among the planets in our solar system, is not only remarkable for its massive size but also for its extraordinary magnetic field, called a magnetosphere, which stretches millions of kilometers into space. Unlike Earth's magnetic field, which is relatively small and gentle, Jupiter's magnetosphere is immense and powerful, dominating the space around the planet and interacting with almost everything that comes close to it. This magnetic field is created by the planet's rapid rotation and its interior, which contains metallic hydrogen deep beneath the clouds. As Jupiter spins, completing a rotation in just under 10 hours, it stirs this metallic hydrogen, generating electric currents that produce a magnetic field far stronger than anything we experience on Earth. In fact, Jupiter's magnetic field is more than 20,000 times stronger than Earth's, making it the largest and most intense in the solar system. This colossal magnetic presence not only protects Jupiter in some ways, but also shapes the environment around it, influencing its many moons, the solar wind, and even the streams of charged particles that travel through space. The magnetosphere is not just a simple static force around Jupiter, it is a dynamic and constantly changing region where the planet's magnetic field interacts with the solar wind, which is a continuous flow of charged particles released from the Sun. When these solar particles collide with the magnetic field, they are trapped and guided along its lines, forming enormous loops and arcs around the planet. This interaction can create spectacular auroras near Jupiter's poles, similar to the northern and southern lights on Earth, but far more intense and vivid. These auroras are visible in ultraviolet light and are constantly shifting, reflecting the turbulent dance between the planet's magnetic field and the solar wind. Instruments like those on the Hubble Space Telescope and more recently the James Webb Space Telescope have captured detailed images of these auroras, showing bright streaks, rings and patches of light that shift and shimmer over time. The magnetosphere therefore acts not only as a shield, but also as a stage for some of the most energetic and mesmerizing phenomena in our solar system. Within this vast magnetic environment, Jupiter's moons also play an important role, particularly the four largest ones discovered by Galileo Galilei in the year 1610, Io, Europa, Ganymede, and Callisto. Io, the innermost of these Galilean moons, is the most volcanically active body in the solar system, and its eruptions eject massive amounts of material, including sulfur and oxygen ions, into space. These charged particles are captured by Jupiter's magnetic field, forming a torus or donut-shaped ring of plasma around the planet. This plasma torus rotates along with the planet and contributes to the intense radiation belts surrounding Jupiter, making the region extremely hazardous for spacecraft and unprotected human explorers. Europa, with its icy surface and subsurface ocean, interacts with the magnetosphere in a different way. As charged particles from Jupiter's magnetic field collide with Europa's icy crust, they can penetrate the surface and affect its chemistry, potentially influencing the composition of the ocean beneath the ice. These interactions may also generate faint emissions detectable by powerful telescopes, allowing scientists to study Europa's hidden ocean indirectly. Ganymede, unique among the moons, possesses its own small magnetic field, creating a miniature magnetosphere within Jupiter's larger one. This interaction leads to complex patterns of magnetic reconnection and particle acceleration, making Ganymede a fascinating laboratory for understanding magnetic processes on a scale we could never replicate on Earth. Callisto, though less active, is still influenced by Jupiter's magnetosphere, as the charged particles slowly erode its surface over millions of years, leaving subtle but detectable marks. The magnetosphere also stretches far beyond the immediate vicinity of Jupiter and affects the solar system on a much larger scale. Its outer boundaries extend tens of millions of kilometers, creating a vast bubble that deflects the solar wind and shapes the planet's space environment. The point where the solar wind pressure balances with Jupiter's magnetic pressure, called the magnetopause, is located roughly 70 million kilometers from the planet on the sunward side, though this distance fluctuates depending on solar activity. Beyond this, the magnetotail stretches in the opposite direction, trailing behind the planet for hundreds of millions of kilometers, even beyond the orbit of Saturn in some cases. Within the magnetotail, charged particles are accelerated and transported, creating streams of energetic particles that can interact with moons and even contribute to faint radio emissions detectable by specialized instruments. The dynamics of the magnetosphere, including its size, shape, and particle content, are strongly influenced by the solar cycle, which takes approximately 11 years to complete. During periods of high solar activity, the solar wind is more intense, compressing the magnetosphere and increasing the energy of trapped particles, while during quieter periods, the magnetosphere expands and becomes less turbulent. Understanding these large-scale interactions is crucial for modelling Jupiter's space environment and for planning missions that venture into this extreme region. Spacecraft that have visited Jupiter, such as Pioneer, Voyager, Galileo, and more recently Juno, have provided detailed observations of the magnetosphere and its interactions. Juno, which arrived at Jupiter in the year 2016, carries instruments capable of measuring magnetic fields, charged particles, and plasma waves with unprecedented precision. Juno has revealed that the magnetic field is not perfectly symmetrical, as once thought, but is distorted and lumpy, with variations caused by the complex flows within the planet's metallic hydrogen interior. These asymmetries influence how charged particles move through the magnetosphere and how auroras form, leading to regions of unexpectedly high energy near the poles. Observations from Juno have also shown that the auroras are not only powered by the solar wind, but also by particles originating from the planet's own moons, particularly Io. When Io's volcanic material enters the magnetosphere, it is ionized and picked up by the magnetic field, forming currents that travel along the field lines and strike the upper atmosphere near the poles. These currents, called Birkeland currents, are responsible for some of the brightest and most dynamic auroral features, linking the planet and its moons in a complex electromagnetic dance. One of the most fascinating aspects of Jupiter's magnetosphere is its ability to accelerate particles to extreme energies, far beyond what humans can achieve in laboratories on Earth. Electrons and ions trapped within the magnetic field can be whipped around at nearly the speed of light, producing intense radiation and generating radio waves that can be detected across vast distances. The acceleration mechanisms are varied and include processes like magnetic reconnection, where magnetic field lines break and reconnect, releasing enormous amounts of energy in the process. Waves propagating through the plasma can also transfer energy to particles, further boosting their speed. These energetic particles contribute to radiation belts that are deadly to spacecraft and pose serious challenges for any mission attempting to explore Jupiter closely. For instance, the radiation levels near the planet's cloud tops can exceed 1,000 times the dose that would be fatal to an unprotected human in a short period, making shielding a critical aspect of spacecraft design. Understanding how these particles are accelerated and transported through the magnetosphere provides valuable insights not only into Jupiter, but also into fundamental processes occurring throughout the universe, from distant pulsars to active galactic nuclei. Another striking feature of the magnetosphere is its interaction with the planet's atmosphere, particularly at high latitudes. The auroras at Jupiter's poles are far more energetic than Earth's, and are generated by a combination of solar wind interactions and internal magnetospheric processes. The atmosphere in these regions is bombarded by electrons and ions, which collide with hydrogen molecules and excite them, causing them to emit light in ultraviolet and infrared wavelengths. The auroral emissions reveal complex structures, including arcs, spots, and transient flares, which are constantly shifting and evolving. These features are influenced by the planet's rapid rotation, which drags the magnetic field around, as well as by the motions of plasma within the magnetosphere. Observations have shown that the auroras can respond almost immediately to changes in the solar wind, with brightening or dimming occurring within minutes. This rapid response highlights the strong coupling between Jupiter's magnetic environment and the surrounding space, making it a natural laboratory for studying magnetospheric physics on a scale far beyond what we can achieve on Earth. Jupiter's magnetosphere also affects the planet's ring system, which is faint and composed mainly of tiny particles. These dust grains can be charged by the magnetospheric plasma and then influenced by electric and magnetic forces, altering their orbits and causing them to migrate inward or outward. The interaction between charged dust and the magnetic field creates a complex and ever-changing environment that is still being studied by scientists. Observations from spacecraft and telescopes have revealed subtle structures within the rings, such as arcs, gaps, and clumps, which are shaped not only by gravitational forces from moons but also by electromagnetic effects. This interplay of forces demonstrates that Jupiter's magnetosphere is not just a distant phenomenon, but directly influences the planet's immediate surroundings, shaping even the smallest particles in its system. The study of Jupiter's magnetosphere is not only important for understanding the planet itself, but also for comparative planetology, studying magnetic fields across the solar system. By comparing Jupiter's massive magnetosphere with the smaller ones around Earth, Saturn, Uranus and Neptune, scientists gain insight into how magnetic fields are generated and how they interact with solar winds and surrounding space. Jupiter's extreme magnetic environment serves as a benchmark for testing theories of planetary magnetism, particle acceleration, and auroral processes. It also helps in understanding exoplanets, planets orbiting other stars, which may have magnetic fields influencing their habitability and interactions with stellar winds. The lessons learned from Jupiter can be applied to these distant worlds, providing clues about their atmospheres, radiation environments, and potential for hosting life. In addition, the magnetosphere is closely linked to Jupiter's weather and atmospheric dynamics. While the magnetic field itself does not directly cause storms or cloud formations, the charged particles it guides can deposit energy into the upper atmosphere, heating it and affecting circulation patterns. This energy input can influence the upper atmosphere's temperature structure, chemical reactions, and even cloud chemistry. Over time, the constant bombardment of particles from the magnetosphere contributes to subtle but measurable changes in atmospheric composition, particularly in the polar regions where auroras are strongest. The interaction between magnetic, electrical, and chemical processes creates a rich and interconnected system that demonstrates how even an invisible force like a magnetic field can have profound effects on a planet's environment. Recent observations from the James Webb Space Telescope have further enriched our understanding of these interactions. Webb-sensitive instruments can detect infrared emissions from the auroras and the atmosphere, revealing details about temperature, composition, and particle energies that were previously inaccessible. These observations complement data from Juno, providing a multi-wavelength view of Jupiter's magnetosphere and its effects. Webb has also allowed scientists to study how the magnetosphere interacts with specific moons, detecting faint emissions and signatures of particle interactions that reveal the ongoing exchange of material and energy. This combination of observations from space telescopes and orbiting spacecraft has created an unprecedented picture of Jupiter as a dynamic, electrically active and magnetically dominated world, where every component, from the smallest dust grain to the largest moon, is influenced by the planet's magnetic might. The magnetosphere's influence extends even to Jupiter's distant environment, including the region where the solar wind meets the outer edge of the planet's magnetic influence. Here, the solar wind slows down, deflects, and interacts with trapped particles, forming shock waves and boundary layers that are complex and turbulent. These outer regions are important for understanding the transport of energy and particles throughout the magnetosphere, and for modelling how Jupiter interacts with the broader solar system. The outer magnetosphere is also a source of radio emissions, some of which can be detected on Earth with powerful antennas. These emissions vary with Jupiter's rotation, the positions of its moons, and solar activity, providing a natural broadcast that conveys information about the planet's magnetic environment across vast distances. Overall, the interaction with Jupiter's magnetosphere is a story of immense forces, dynamic processes, and constant motion. From the depths of the planet's metallic hydrogen interior to the far reaches of its magneto-tail, from the fiery volcanoes of Io to the icy oceans of Europa, every part of the system is linked through magnetic and electrical connections. The magnetosphere channels energy, shapes auroras, accelerates particles, and influences moons, rings, and even the outer solar system. It is both a shield and a laboratory, a source of danger, and a window into universal processes. Studying it teaches us about magnetic fields, charged particles, planetary atmospheres, and the fundamental physics of space. Jupiter's magnetosphere is not just a feature of a planet, it is a dynamic, living system, a cosmic engine of energy and motion that reveals the hidden power and complexity of our solar system in ways that are both humbling and endlessly fascinating. This enormous and constantly shifting magnetic environment reminds us that planets are not isolated objects drifting silently in space. They are active, interacting, and interconnected with their surroundings. Jupiter's magnetosphere in particular is a vivid demonstration of how magnetic forces shape worlds, influence distant moons, and create phenomena that inspire awe and curiosity. As technology advances and missions continue to explore Jupiter and beyond, our understanding of this giant's magnetic kingdom will only deepen, revealing ever more intricate patterns of energy, motion, and interaction that illuminate the workings of not just one planet, but the fundamental processes that govern the universe itself.